save some of the comments that I was gonna. It was more like a summary of what was presented yesterday. Ah, no. Sí, es que me tengo que pegar mucho aquí el micrófono. Okay, so today on the schedule we're gonna get started with. We're gonna skip a few words that I was gonna say in terms of summary of what was we covered yesterday. But really, yesterday was a presentation of ideas, and there was nothing really, no conclusions or anything. So it's not so important, and. So we want to save up some time, and we still have to cover the last presentation from yesterday that we didn't have time to cover. So we're going to start with that one. So it's going to be Jorge Morales that's going to talk about the historical tsunami of southern Peru in 1868. And we're just waiting for his presentation, either a computer or they will be showing his presentation from the computer room. Do you know what the situation is, Ricardo? Are they gonna bring a computer? Oh, okay, there you go. So they're bringing a computer.
Good morning. Yeah, it's okay. Listen. Shall I start? Okay, thank you very much. I will present the historical tsunami of southern Peru of 1868, sorry. So the content of my presentation includes some introduction, a little background, some seismic sources about that earthquake, the simulations about that seismic sources, and some results I have found. First of all, a little introduction about this event. Well, not about the event, about just general about the earthquakes. This chart.
Can you share the presentation in the Zoom, please?
Sorry.
I think
in
the
Zoom.
screen
Okay,
is not being shared in Zoom.
Okay. No, I think they did not. Okay. No, there's no Zoom. Sorry for the participants around the world. Oh, sorry, Eric, right? Sorry, Eric.
Yes, sorry.
Yeah. So yeah, for the participants around the world, they are not watching the presentation. Okay. Can you see now, Eric?
Yes, I can see. Thank you.
Okay, okay. So, shall I continue? As I mentioned before, this is just some map about the people affected by earthquakes up to 2010. As you can see in this world map, the Pacific zone has some, well, a little or a lot of affected people around the world. Peru, Chile, more Chile in these recent years, as you can see. Also Japan and these countries. So just some general context about the earthquakes around the world. And also this chart, I don't know if you can see, it's a little bit small, but in the left right hand we have some people affected by earthquakes around South America. So Chile is yellow one and Peru is this light blue. So as you can see here in 1970, this is the earthquake of Ancash, which has the snow slide. That's why in Peru there are so much affected people. This is just affected people, but not death, just explaining. And in here we have also the economic damage share of in GDP. So this is just because I want to explain that it's not only affected people, but also a lot of economic losses, right? So in here we have the earthquake in 2010 in here in Chile, a lot of economic losses here as well in affected people. Around almost 3 million of people affected by this earthquake. Well, this is just general context about the earthquakes, and this is in Peru as well. This is the 1970, and this is the Arequipa earthquake, and this is the Pisco earthquake. Yes? Oh, okay. Oh, sorry. Oh, I'm so sorry. I'm going to put the okay. Now you can see it? Okay. So yeah. So sorry. Thank you. Yeah, but it's not showing in the screen. Yeah. Here's yes, but yeah. I will use this. See, yeah, it's better. Okay. Thank you. So as I mentioned, this is the earthquake of the 70s in Ancash. This is the 2001 Camaná that Dr. Jimenez showed yesterday, and this is the Pisco earthquake in 2007. And in here in damage in the share of GDP. Okay, let's continue. We have here the historical large earthquakes that have produced tsunami around the around Peru and also some part of the northern Chile. The earthquake that I'm going to explain today is the 1868, right here. As you can see, it's more than 4 degrees of length, so it's huge earthquake. The other large earthquake that has happened in Peru is the 1746, right here. The 1868 is even larger than this one. As you can see, this is the 2007, 2001, and so on. So let's start with some general content about the 1868 earthquake, Arica earthquake, and tsunami. Occurring August 13 at 4:45 p.m. According to the some periodistic information, that the intensity was around 11 in the Mercalli scale, and was accompanied by a tsunami in southern Peru and some northern Chile as well. Well, in this case, Arica and Tarapacá were part of Peru yet. Okay, so the Dr. Polo refers to this earthquake as one of the largest that have been verified in Peru since its conquest in the 80s. Microseismic observations indicate that the epicenter earthquake was near the port of Arica, and the movement was perceived up about 1,400 kilometers to the northwest of Peru in Samanco, and the equal distance to the south, almost up to Valdivia, Chile, for the south of Arica. And up to a few 200 kilometers to the east in direction of Cochabamba, Bolivia. So as you can see, this earthquake was felt almost 700 kilometers around. It was a huge earthquake. In Arequipa, felt most of the temples felt. The new portal, the local of Cabildo, and many public and private establishments were destroyed and stay in ruins. These pictures are very old, but as you can see, this is the Arequipa Cathedral, and it's all fell down. This is the Arica port as well. Well, maybe the pictures are not as good, but let's consider that it is 1868, that's why. The earthquake, of course, was followed by a great tsunami. In Arica will be like this 1737 hour when impetuous overflow of the sea was observed, and the first wave reached a tide of almost 12 meters according to the some writings, and swept completely the port, taking everything that found in the way. Just a little more information. This is all according to Silgado Ferro. The first wave lasted about 40 minutes, so it's a period of around 40 minutes, and at 1850 the sea broke it again with waves 16 meters high, according to the again to the periodistic information. The third wave, the most violent, invaded land at 1710, which is the Peruvian corvette America. So this is a ship of about 1,560 tons. The Watery and the Fidonia Gate of the USA. This is another ship from the USA, which were thrown 30 meters inland. So as you can see, the power of destruction of this wave was huge. Again, Polo mentioned. Okay, sorry. Polo mentioned that this lasts up to 7 p.m. and despite there was or dark, it was believed to perceive 3 more waves of intensity that decreased 26 minutes after this time. When just some information about the destruction or the people who have died for this earthquake. In Chala, for example, 30 people was found dead. In Arica, around 100. In Iquique, around 200. And also the wave was felt in California, Hawaii, Yokohama, the Philippines, Sydney, and New Zealand. So there were a lot of destruction around these places. They were counted as almost 400 movements of aftershocks until the August 25th. So this is just some general information about this earthquake. Most of this information was from, according to Silgado Ferro in his paper of 1978. So what did I do? This is the historical event, as I mentioned, of 68, sorry, was a giant earthquake. This magnitude is, as someone said yesterday, depends who you ask. In this case, is around 9.0 NW, struck the southern Peru and the northern Chile, generating a huge tsunami. So this is, I'm going to simulate the occult that actually I think this after me is going to present. So this is the source of occult of 2006, and this square shows all the places that have affected according to what I explained before. These are the last. These are the last tsunamigenic earthquakes that have happened in the southern Peru and north of Chile. This is the 1868 earthquake. This is the 1877 earthquake, and showing the epicenters. This is the Camana earthquake in Arequipa and the Pisco earthquake in 2007, and also the Iquique earthquake in 2014. So I think somebody already showed this. This is just the GPS measurements around the area. And according to this, also Dr. Pulido in 2014 generated 12 earthquake scenarios, sleep distributions. So this is just trying to find a future event in the area. So this is the coupling. So this is the area where the coupling is almost around 1. And well, also here is it's not considered yet the Iquique earthquake that happened around here. So this area should be clean by now, but in this case it is in 2011, so all this area was with all asperities. Some vulnerable cities around the area that would be that were affected and will be affected again if this earthquake, because you know, right now still we have the coupling in one, so this is a seismic gap. So for example, Ili district in southern Peru, this is an area with almost 66,000 inhabitants, and this is an area which principal economic activities are fishery, mining, and port activity. As you can see, in summer, this would be all crowded like this. And some comments about this area is that the topography is very flat. So this is, if the earthquake happened in summer, that would be disastrous. Also, Arica City could be affected. This is Arica City, where we are right now. This is the area. Well, this population is the whole population, but in coast area should be around 20,000. I'm not quite sure, but this is the total population in Arica City. Also, the economic activities are fishery, mining, and some other port activities. And also in Ilo, we have a thermal power plant that also could be dangerous if the earthquake will affect these places. Well, let me show the historical source that I mentioned before. This is Ocal source in 2006. He considered two sources, homogeneous sources. Yesterday we were talking about the homogeneous sources that maybe are not the best, but in this case is an earthquake of 1868. So we have not much information, and these sources were generated based on some stories that were told before. So they say in Arica some 14 meters, in some places other meters. So what Ocal did was just consider that tsunami heights in order to generate these sources. And this is where the NW estimated by Kanamori's formula, of course. In this case, consider just this single fault would be 8.9, and consider these two faults would be up to 9.1. So in this case, I simulated this considering just the single one and these two. And on the other hand, this is the Pulido's fault, Pulido's lead distribution, sorry, according to the GPS measurements, and the moment magnitude is around 8.5. So in here, we can see the enormous large of the Ocal's single fault. It's very huge, and well, this is the Pulido's. Because in here, Pulido considered the 2001 Camana earthquake. So the fault is not considering this length. And it's quite more realistic, I would say. Well, this is just the data for the simulation, considering these two faults, as I mentioned. These were simulated using the Tsunami N2. And I think in here, can you see the video? Yeah, there are the videos. This is the single fault, and this is the two faults. And we can see here the simulation. The heights were up to 15 meters, I think. So, and here I can show you the comparison about the results that Ocal obtained in his simulation in 2006. He considered a resolution of 90 meters. I did it at 30 meters using mainly SRTM topography. And as we can see, are quite consistent, although in here I think I got some more large results. But then I did a validation with the some results that the Institute of Computational Mathematics from the Novorinsky, Russia got of this earthquake. And as we can see, this is the recorded, and this is what I computed with my simulation. And in general, is quite consistent. So this is the single fault, and this is the two faults. So in Arica, the 15 meters, in here we have this. I think this one, yeah, is the single fault, yes. well, the sleep model. Oh, then let me now present the model of the Pulido. He did 12 sleep models. They would be like the future event. He did 12 sleep scenarios. So in this case, what I considered in this case, this was my master work, and what I consider was there are 12 scenarios. What should I use? Of course, maybe the best thing would be that I maybe simulate all and do the envelope. But what I did was something different, because actually I have actually a few time at that time. So what I did was I did the seafloor deformation according to Okada, and I computed the volume of water displaced. Of course, this is not the best thing that maybe we can do, but in case of we have few time and we have to compute something fast, what I did was to calculate the volume of water displaced, and I found that the scenario 11, in this case, displays more water. So yesterday, again, Ignacia was saying, why? What is good and what is not good? So what can we do really? So of course, the best thing is if maybe we do real time, but in this case it's 1868, so we cannot do it real time, and we can do a lot of things, and then discuss about the results. So what I did was simulate the 11 scenario, because I found that displays more water. Of course, at that time I found that was okay, but now I know that maybe I should consider where the places where the asperities are closer to the area I'm thinking I'm going to affect, in the worst case scenario, of course. But well, in this case, just the tsunami height is around 6 meters, so it's quite few. And when these are some results, in the end, with the sources 1 and 2, I found that the results, as I mentioned in the chart before, they are quite consistent with the periodistic reports. This is just some inspection, let me show. And this is the max velocity, around 10 meters. And also for the plant of power, in here there are not so much inundation. As I mentioned before, this is the topography. This is the inundation for the Pulido fault. Almost no inundation, as you can see, which is good, because this is actually the most realistic according to the GPS measurements, but we don't know what will happen actually. So, and as I mentioned before, this is the topography. As you can see, is very flat at first, and then there are as is inverted. This should be positive. So it's flat at the first 100 meters, and there is some steepness in here. So in case of Ilo City and around, the first 100 meters is very flat. So if an earthquake would happen in summertime, that would be a little bit very, very dangerous. And again, the velocities according to the Pulido fault, they are around maybe 7 meters per second. And well, yesterday I did a simulation very, very fast about this, also Arica coastal area. This is Arica, again 30 meters, a little bit, a simulation very fast. And I found that this is much southern from Arica, sorry, for the other part, because the Ocal fault, let me show you just once again. This is Ocal, so is almost in the southern Peru. Arica is around here, so that's why almost no inundation in Arica. And where is it? Okay, this is this inundation, just in some few inundation around here. And actually, for your tranquility, the hotel where we are staying is around here, so according to my simulation, there is no inundation around the hotel, so this is good. Yes, and I think that would be all. Thank you very much.
Any questions for anybody for Jorge? Yes, we have here one, Ignacia.
Hi, thank you for your presentation. I have just one question. Don't worry, it's not regarded to the source. Why do you think there is that difference between your model when you put the hay wave with the pulido? No, yeah, okay, before. There is one point that is very different. It's a very high amplitude, and you don't reproduce that. Why do you think this? And then the left, like the very big one, yes.
Thank you for the question. Yes, I also found this. I think is because we use a different bathymetry and topography, and then this. I think that would be the main reason that is different in this part, because I used some charts from the fishery ships in Peru, so I did a little different bathymetry, and so in this case I have some few differences. But the topography I think is almost the same. I use SRTM, but the bathymetry I changed it, and also the resolution is 30 meters and Ocal did 90 meters. Yeah.
¿Cómo? ¿Puedo entrar? Sí, puedes entrar. Y voy a hacer un cafecito. ¿Quieres tú?
Sí, sí, por favor.
¿Ah?
Could I ask a question, please? I would like to ask a question, please. What is the magnitude of the earthquakes that you have chosen here?
Yeah, I have a chart. And where is it? I think it's before. Yeah, the magnitude computed according to the fault is in here. So it's 8.9 for the single fault and 9.1 for the two faults. And this.
But not for this. For this. Yes, for this.
Yeah,
for all the earthquakes you have shown, all the.
Yes, this
okay.
is 8.5 calculated according to the distribution. Yes.
Okay, because regarding the length of the rupture, it seems.
Yeah, the disparities in here are quite big.
Yes. A little too large, but. Okay, and what explains these differences in the slip distribution that you are showing? Is it the starting point of the rupture? Is it what is the parameter that control these differences in the distribution?
Well, actually, I just use it from Pulido, and he was the yeah. I'm sorry, I'm not the seismology. Maybe I cannot explain that. Yeah.
Okay, thank you. Very nice job, actually.
Gabriel had a question here.
Thank you, Jorge, for your presentation. I'm not sure to follow very well to understand, but at the beginning you mentioned that some chroniclers tell about 16 meters of tsunami high at Arica, something like, and in your models you got only, I don't know, 10 meters or 12. What do you think about that? Because there are some chronicles and other reports even tell about 20 meters of inundation at Arica. And what do you think regarding your results and this seismic rupture source, in fact?
Yes. Well, according what I mentioned was around 15 meters in Arica. This is what this laboratory computed according to what they read. Yes, and in here, in order to accomplish many places, because that's what Ocal did, according to his paper, he modeled this homogeneous fault to get the height in all these places from north to south. So if he wanted to get these 15 meters in Arica, maybe he should have done it a little bit larger to the south, and maybe not so a little bit shorter in north part, and maybe he could get these 15 meters, but in the northern part, maybe not accomplish these places in Ilo, Islay, and Mollendo. So yeah, the source is like this, as I mentioned. So he did it in this part. Yeah, in order to accomplish, maybe he could have done it a little bit larger, but I think what he did, and maybe we can ask him later because he will explain later, yeah, is to accomplish the tsunami heights in these northern parts of the source. Yes, I think that's according to my understanding. That's why it not accomplish that 15 meters in Arica. Yeah, and that's why also he put another fault in here. But just mention that here is the Nazca Ridge, so it's a little bit maybe not so realistic that the earthquake will trespass this Nazca Ridge. Well, because there are no historical information that a fault has trespassed this Nazca Ridge.
Okay, Emil has one last question.
Just for the record, and as I mentioned already yesterday a little bit, the fundamental point in our study was to try to explain why the tsunami was so devastating in Pisco. And that is not part of your database, essentially. And so in order to have something which is interpreted as being between 5 and 10 meters at Pisco, you need to push the fault north. Now, as far as jumping the ridge, I know this goes against the canons of some models of plate tectonics where ridges such as the Nazca Ridge are barriers. The barrier is just as good as an animal doesn't jump it. And there are other examples, for example, in the Solomon Islands or in Mexico, of ruptures which have gone through things which are thought to be barriers, like triple junctions of plate boundaries. So that was our model. Now, regarding Arica, we were not particularly interested in modeling the situation at Arica. And of course, if you push if you put 100 kilometers more to the south and you tweak your data, you'll probably get higher waves at Arica. That's possible. So I just want to say that certainly the aim of that paper was not a full modeling of everything available, because for one thing, we didn't have all this data at that point, but we were focusing on the question of Pisco.
Right. Thank you very much.
Okay.
Thank you.
Thank you. And thank you, Jorge. And Emil, now that you're at it, your turn. So you're up next.
More technology issues. I could try to give a talk without slides. So what the purpose of this talk is really is to try to look at the challenges which face us. Ever since we developed plate tectonics and we started understanding how the Earth works and why we have these big subduction earthquakes, which create tsunamis, we think that we have a model that explains everything. But this model has some very definite challenges, and I would list about 3 or 4 in my talk if I have the time. The first slides in the talk would show you the general pattern. We all know it. We have 2 plates which collide. The collision, results in the buckling of a plate, the deformation, and you start deforming everything, and you accumulate strain until it snaps. And when it snaps, it creates a big earthquake which moves the ocean. And here comes a tsunami. So we all understand this. However, the first challenge, which was identified, put in focus, many people knew about it, but it was put in focus by Seiya Ueda and Hiro Kanamori in 1979. And the first challenge is that not all subduction zones are created equal, if I may say. You have variations in the nature of that contact, in the nature of that collision. One end member is South America, it's Chile. So what you have in Chile is you have plates which are involved in a very, very strong collision with a lot of coupling at the interface. Why is another question for the time being. And as a result, the coupling is very strong. The deformation is going to be very strong. You build the Andes, you build a wedge at the bottom because you scrape the material from the ocean floor, so you find all this oceanic material in the Andes that Darwin described many years ago, and you also flex the plate before it gets to the subduction, and you end up with enormous earthquakes. So that's one end member. The other end member is what happens in the Marianas, for example. In the Marianas, you have very loose contact. And so the plate is old, actually, so it's heavier when it dips and it falls, and it doesn't have much incentive towards colliding. The end result, wonderful. So we can go, thank you very much, appreciate it. So we can go to maybe 2 or 3 slides, basic story. So next, if you give me these. So in the Mariana's case, we have very little coupling, and that results in a smooth subduction with earthquakes which don't go very much over magnitude 7, even though. Okay, so thank you. All right, oops. Oh my gosh, good Lord. All right. So, yes, we had here this thing. Maybe if we have full screen or something. So you see, in the case of Marianas here, we have weak coupling. We don't have very large earthquakes. And essentially, we know very few, or at least Ueda and Kanamori knew of very few tsunamis originated from such places. The next item of business is to try to understand why. Why is it that we have different subduction zones? And there was a paper in 1980 by Ruff and Kanamori, which said it's all a question of the age of the material, because the older the material, the denser, the colder it is, the denser it is, and so it wants to sink, so the coupling becomes less, and also the rate of convergence in centimeters per year that you have. If you have few centimeters per year, you have little coupling. If you have many centimeters per year, you have stronger coupling. So you put together these two, and you give me those 2 numbers, wonderful. Wonderful, thank you very much. But, all right, so we are here at this fundamental diagram by Kanamori on the left, Larry Ruff on the right. In those days, people had long hair, you know, that was fashionable. And Seiya Ueda as a reference on the bottom because he was behind this. So give me the age here of a material which subducts. I don't have a pointer, so the age goes that way, the rate goes that way, and I will tell you what the maximum earthquake you can have is. And this was published in 1980, and for 25 years, close to 25 years, I taught this in my class. The students had better know this if they wanted a good grade in the class, right? So it was, in a sense, I wouldn't say the Bible, but it was the scripture, if you wish, of how things work. Now, the problem with this came with Sumatra, because Sumatra plotted here in the diagram where your maximum magnitude should be about 8.2, and we all know that Sumatra was something like 9, so it should be somewhere here towards the 9 earthquake rather than 8.2. Huh. So maybe it's the exception which confirms the rule. You know, you have this concept of the exception which confirms the rule. So I was still, after Sumatra, I was still teaching this, but the problem is that if you look at Japan in 2011, you have the same story. The Japanese earthquake plots where it should be at the most about 8.2, and actually it's more like 9. So I stopped teaching it. And if you look at more of this data and you look carefully, you have so many exceptions which confirm the rule that there is no rule, really. My colleague Seth Stein and I, we reworked this. We said, yeah, but you know, since those days, we get better estimate of the age of the plates, we get better estimates of the rate of conversion, so let's replot everything. And the problem is, if you do this, you go from a correlation which is about 0.8 here to a correlation which is about which is 32%. So 80% you can tell the reviewers of a paper it works. 32% no. Okay, so we have to live with the fact that this is over. Now we try to find a better mousetrap. You know, you try to find better mousetrap here, and one of the things we did, or at least I tried to do, was to get rid of the rate of subduction, consider only the age of the plate which was subducting. And one day, and you have a box here which is empty. This is great. If you take old material, you don't find big earthquakes. So here we have something. And one day I was drinking sake, ouzo with Kostas Sinorakis on a beach in Greece. I said, Kostas, I need a Greek word for that. And he came up with lithopaphsis, which means lithopause. You know, at some point the lithosphere becomes so old that it cannot create big earthquakes. So I was about to write up this thing when the Tohoku earthquake occurred, and bing, it violates the concept and it no longer works. So forget this. And then there are other things. I don't have much time, so I will pass this, but the idea that sediments can play a role, also that was an idea that Dave Scholl put together, but in the end it doesn't work. And so we are left with find other ideas. I mean, you're welcome to find them, but for the time being, we have to live with the fact that we should consider that all long enough subduction zones could entertain a very big earthquake. And even, for example, I didn't have much time, but even in the Marianas, which we looked at this, you know, we considered to be an end member with no tsunami danger, essentially. If you look at some very old reports, historical records, there seems to be something in the 1820s which has to be a big tsunami-genic earthquake in the Marianas. So we have to live with this. Second challenge, the infamous tsunami earthquakes. We've all heard about this. These are earthquakes which were defined by Hiro Kanamori in a 1972 paper as events whose tsunami is bigger than what you would expect from the seismograms, from the seismic studies. and in particular from the conventional seismic studies, conventional magnitudes. Typical case is Nicaragua in 1992. This earthquake, at some point, you know, I've heard this before, and we all know this is the message we pass to the populations. If you feel the earthquake and if you feel an earthquake, you're close to the beach, run away. Yeah, but in this case, the earthquake was not felt at some beach communities, and 40 minutes later the wave came, killed 170 people. So there was something wrong with that earthquake. And this something wrong is that the motion was slow, so it was deficient in the high frequency that people feel or that destroy buildings, that shake the area. And it hides its power. It has a spectrum which is what the physicists would call red-shifted, which means it's shifted towards the low frequencies. It's like if you play only the bass in a concert. And you can have a lot of energy in the bass, but you don't hear anything in the trebles. So here is a list. This is a slide which I used. I'm sorry, I used it for a talk in Indonesia, so it outlines Indonesia. But starting with the charter events that Kanamori identified in his early paper, which were historical events in Sanriku and the Aleutian Islands, we are now about somewhere to about 20 or so events. In green, I'm mentioning what I call primary events, which are earthquakes, tsunami earthquakes, which occurred as main shocks, if you wish. And in blue, I have aftershocks, which are tsunami earthquakes which occurred as aftershocks of regular earthquakes. There were some models which were proposed notably by Fukao in 1979, which said, well, you may have a regular earthquake here, which doesn't reach the top over there, and later on there is an aftershock which propagates into this wedge. This wedge probably is some sedimentary material which is of lower quality, so the rupture is slower, and so the spectrum of the earthquake may be redshifted. So that was a model for the aftershock tsunami earthquake proposed by Fukao. Then there was a model proposed by Paulette and Kanamori, and actually earlier on by Tanioka and Satake in Japan. And they said, well, we have an earthquake which propagates here, but the contact in a place where actually it's sediment starved, there are not too many sediments, so the contact is irregular, and the rupture is jagged. You know, it goes from asperity to asperity, and if you integrate this over some time, it looks like a slow rupture. And that could explain places like Nicaragua in 1992, Peru, Chibouté, Peru in 1996, which occur in area where you don't have much sedimentary material to glue the contact together. What can we do? What can we do is try to look at the P waves. This is the P waves of Java, I think, 1994. And what you see, if you're a seismologist, what you see here is that the P waves are extremely long frequency. This is 100 seconds, so the main energy here is really at something like 10, 15 seconds of period, not 1 second like you would expect for typical P waves. And so maybe we can compute something which would be the energy which is released in these P waves and compare it to the seismic moment. And this was an idea which went back to Boatwright and Choi in the 80s, and which I developed later in the 90s by systematically computing the radiated energy. This is a log plot, by the way, radiated energy as a function of seismic moment. And you see that the 3 tsunami earthquakes that we had at the time, they plot definitely towards the bottom here. This is the mainstream events, you are deficient by 1.5 logarithmic units. That's a factor of 30. And so these 3 tsunami earthquakes that we had at the time clearly can be identified in a diagram like this. Right now this diagram has progressed, and this is the list of all the tsunami earthquakes that I've studied in the area, and you see how they are very definitely deficient in this energy to moment ratio. And by contrast, the blue earthquakes would be very snappy. They would be displaced towards the high frequency, they would be blue shifted in energy, and they would be extremely destructive, but they would not create very large tsunamis, at least in principle. For example, the Christchurch earthquake in New Zealand here would belong to that category. They are usually intraplate earthquakes rather than interplate earthquakes. So this method has been developed and is used in some, I'll pass on this, is used at some tsunami warning centers. You can also follow the progress of moment here, the moment computed at various frequencies. And you see, for example, in the case of Sumatra, which has the characteristic of some tsunami earthquakes, you see that the moment starts increasing with longer periods, lower frequencies here dramatically towards 400, 500 seconds. So that's another characteristic. Finally, you can look at the duration of a P wave here and relate it to the energy in the P wave, which has the advantage that you can do all of this only on the P wave train. So what you do is you filter the P wave like crazy between 2 and 4 hertz, which is really outside of what we usually consider in seismic studies. We are more like 1 hertz for P wave, and you try to look at the duration, and you see in the case of Sumatra, for example, how extremely long this duration is as compared to the Nias earthquake a few months later. So we can implement this, compute it systematically, compute the duration. I developed an algorithm to do this, and then you can plot it as a function, for example, of seismic moment, and you see how these guys here plot on top of the line. This is again a logarithmic unit, so they plot systematically on top of the line here. Andrew Newman, who was a former student of us at Northwestern University, he developed this in real time, and he implemented a method which essentially is very similar. And you may get, if you are subscribing to Tsunami Bulletin Board and things like this, you may get messages from Andy Newman where he identifies these earthquakes. In the case of Mentawai, he was able to issue a warning of an anomalous earthquake only 17 minutes after the origin time. Unfortunately, it was not operational at the time, and it was not used by the warning community in Indonesia. You can also look, I don't have much time, but the hydrostatic waves, which go, the hydroacoustic waves, which go into the SOFA channel of the ocean, which are known as T waves, very high frequency waves. In case of a tsunami earthquake, they'll be completely deficient here. Look at that, as compared to a regular earthquake. I think this is the case of the 296 Peru earthquake. This is the Chimbote earthquake, which is a tsunami earthquake. This is a regular earthquake in Nazca a few months later, at the same station, same geometry, and so on. And you see how different these two are. And so you can try to quantify this. And I developed also an algorithm which shows here that it correlates very well this measure from the acoustic waves, the hydroacoustic waves. It correlates very well with things like the energy to moment ratio and so on. Question: where do they occur? Answer: everywhere. Okay. You see here the Pacific. You find these tsunami earthquakes, primary events or aftershock events. They are omnipresent. It doesn't seem, even though we don't know them, in the coast of southern Peru and northern Chile, we haven't seen them yet. But there is no reason to believe they could not occur there. Okay, enough said about tsunami earthquakes. That was one challenge. Third challenge is the irregular fragmentation of rupture, and this concept that you have a big subduction zone, and sometimes it ruptures in big earthquakes over long faults, and sometimes it ruptures in small earthquakes. And it goes back. We can start with this model, which is very simple again, of the loading of a stress here, the locking of the interface, and then at some point it snaps, there is the rupture. And a very simplistic argument, which is true, which is perfectly true on geological times, you know, hundreds of thousands of years or so, is that you load and it sticks and you slip and it sticks and it slips and it sticks and it slips. So you have a concept of a periodicity, in quote, okay? There should be some kind of periodicity of the earthquake cycle. That's very good, but as always in physics, you have some kind of error bars, uncertainties, so it loads up to a certain point, and the point at which it ruptures, you have a plus or minus error there. You cannot tell. This is going to be more or less random. And the same thing is true. Are you going to release all the stress, or are you going to fall somewhere here in this plus or minus range? So you see that depending on the location of a rupture in this band and the location of the remaining stress here in that band, you may have bigger or smaller earthquake. And this one is going to be early here because you rupture sooner, and this one is going to be early because you start at a higher level of stress, and this one is going to be late, and so on. The big problem here is that this uncertainty, which is shown over there, with respect to the regular periodic release of earthquakes, this uncertainty is on the order of anywhere from 10 years to 100 years. So 10 years to 100 years, if you are a geologist in the business of looking at at the very long-term behavior of the Earth, it's nothing. But if you are a human being, it depends whether I'm going to be affected or my grandchildren are going to be affected. And that makes a big difference in terms of, number one, evacuating a city, because you cannot evacuate a city for 100 years, or building something. You want to build a nuclear plant, you want to build a hospital, a big port facility or something, a gas exporting terminal. You are thinking about something on the order of 50 years, 100 years of lifetime of a facility like this. So it makes a big difference. So that means that these error bars negate completely the principle of periodicity of earthquakes on a human scale. That's a big problem. Now, in 1975, Ando wrote a paper which I think is a landmark paper by studying earthquake in the Nankai Trough in Japan. And what he proposed, he said, I can identify 4 blocks here. This is the main Honshu Island. This is Shikoku, I think. Kyushu would be here, and Kyoto would be somewhere over there. Tokyo is about here. And he observed that the earthquakes had an irregular pattern. Occasionally, you had a very big earthquake. The last one is the Ohei 1707, which he thinks ruptured the entire thing. And then in 1854, within a month or so, there were 2 earthquakes which each ruptured 2 blocks, A, B, and C, D. Then this one ruptured only C. Then this one ruptured A and B. And it is expected in Ando's paper that D would be up. And even though it's been 50 years since that paper was published, this hasn't ruptured yet, but D hasn't ruptured in a long time. But who knows? Maybe the next time it will be ABCD. Maybe it will be CD or something. And Ando's point was that it was completely random and unpredictable. And the big difference is this moment magnitude, which is written here. It doesn't look like much, but if you go from 8.2 to 8.6, in terms of a tsunami, it makes a big difference. And if you have a scale of tsunami deaths here on the right, you see that you go from 1,000, which is bad enough, to 30,000, which is catastrophic, estimated for 1707. So the lesson here is we don't understand that. There is an element of randomness, and it's not even sure when the rupture starts that it knows what's going to happen. Obviously the rupture started here somewhere, and it was progressing, and somehow it found an asperity, it found a barrier of some kind, an asperity, and it decided to stop to wait 2 weeks until the next one. And the problem is we don't understand what controls that, whether that barrier will be jumped or not. Now, this was a paper by Ando in Japan, and this was shown to be the same, including from Terremoto tsunami studies in North Japan and the Kuriles, and in Cascadia. After they discovered the 1700 earthquake in Cascadia, they went and they found many, many more before, and they found that some of them were big, some of them were small, and some of them clustered in time, and so on. And of course, also in Chile, this is our colleague Marco Cisternas in one of his holes he digs, and it was found notably in Chile that when the 1960 the earthquakes which were before the 1960 event were not carbon copy, and some of them were smaller because they had extended over a shorter distance. And that was very important because there was a paper by Kanamori in 1977 where he was plotting the slip as a function of the recurrence time here, and he was claiming that, well, the seismic, the Chilean, that was for the Chilean earthquake, he had very large error bars, and at that time his line of observed plate motion just about crossed here. But then the plate motion was revised, and you had this very unfortunate situation where you had too little plate motion to explain the Chilean slip rate. And that was a major problem, which was pointed out by Seth Stein in 1986 and collaborators. And of course, if you now assume that, well, the 1960 is okay, but the previous ones were smaller, and so the recurrence time is not really 150 years as suggested, but it may be longer. You catch up with that line and you save the day, in a sense. Okay, so Ando's concept and Cisterna's data, they save the day for this thing. But the main lesson to be remembered, the take-home message, is that earthquake repeat is capricious. Capricious being a very nice word to say we don't understand it. Mother Nature probably has its deterministic arguments to control it, but we don't understand them. So we say it's capricious. And another case of interest, for example, on which I worked is in the Indian Ocean here between Iran and Pakistan. There was a very definitive, very large earthquake in 1945, for which we were able to do a survey because there were old people who remembered it yet when I worked there in 2010. And you find in the literature that there was one in 1864 and one in 1765. So you get the feeling that you have blocks A, B, C here. There are some old reports that perhaps in 1483 there was a D block. Who knows? And the problem that we face, and I've worked with Iranian colleagues on that, the problem that we face is, could we have a rupture which would be, you know, ABCD, or even ABC would be bad enough, which would be bigger than the 1945, which is again a completely open question. Now, another thing that I want to mention is, as a challenge, is other events. Not all earthquakes at subduction zones are subduction earthquakes. You can have earthquakes which are close to subduction zones, which can be very big, like outside in the plate there. 2012, there were two here, which were off the coast of Sumatra. There was strike slip, so they didn't do much tsunami, but it is a concern that we must have. And in particular, you have the normal faulting earthquakes, which can occur under several geometries. For example, here in Sumbawa in Indonesia in 1977, you have an earthquake which ruptures the place, which cuts the place out in the ocean there before it subducts. And it's a normal faulting earthquake. And this thing was huge. I think I have no, I don't. I think it killed, the tsunami killed several thousand people in Sumbawa, which is an Indonesian island, and it did some damage in Australia, where there is not too much population there, but still it was observed. Now, there is another possibility where you can have an intraplate earthquake in the plate here, where the plate breaks after the subduction interface. Below it, inside the plate, you can have an intraplate earthquake in Tonga in 2006, for example. And these guys, they're never going to get into the budget of the centimeters per year and all that, because they correspond to something completely different. But you have intra-plate stressors here which are going to break the plate. Or you can have in places where you have a lateral heterogeneity along the subduction with different dips, you can have a motion between one part and the other here. It looks like a pair of pants, see, with the two legs, and you can have a seismic motion. And this was the case, for example, in the Kurile arc. And some of these events, especially this kind, can be tremendously lethal in terms of tsunamis. This is the case for the 1933 event in Sanriku in Japan, which was outside, out there in the Pacific plate, and it definitely has a snappy character. We plot it here on my diagram, which means that it's definitely not the kind of tsunami earthquake, but it's so big. This was a magnitude, I don't know where it is. This is moment, so this is a magnitude 8.4. So in terms of MW, and the tsunami killed 3,000 people in Japan. Okay, it was far enough that the shaking didn't kill too many people, but the tsunami killed 3,000 people. And for a while, it was considered one of the most significant death tolls from tsunamis during the 20th century. So it is very important. Significant damage in Hawaii. I don't think there were any fatalities in Hawaii because there was a man by the name of Tom Jaggar, who was the director of the Hawaiian Volcano Observatory, and he issued a warning. And he said there is a tsunami coming, and the people believed him, and they got out of the way. But they couldn't get all the boats out of the way, so it was very significant damage in Hawaii. Now the problem with these guys is that essentially, and this is the case in 77. This was actually, I should have showed it earlier, but this is the case in 77. This was actually one of the first tsunami surveys which was done systematically afterwards, and the waves reached 15 meters in Sumbawa, and there were several hundreds, if not thousands, of people killed. And this is some of the field work done afterwards. Now the problem with these guys is that we know nothing about the recurrence rates. Okay, we have some idea of centimeters per year as far as the convergence in big subduction events, in the interplate events is concerned, but what is the recurrence rate of such earthquakes? We cannot start to answer the problem, because if we plot them on a map, I think it would be fair to say that the big ones that we know of this kind, if we plot them on the map, we do not have more than one per province, all right, known in the instrumental record of seismology. So go figure a recurrence rate of something which corresponds to the internal deformation of the plate, and we don't have GPS, motion bottom GPS to monitor this. Go say something about this. When you have only one event in each province that you know of. So in South America, I don't know that we know any of these outward normal faulting events in the Pacific Ocean in South America. But that doesn't mean that it may not come one day, and it could have very, very tragic and lethal consequences in terms of a tsunami. And the problem is also that despite all the progress that we've made in terms of trying to forecast and of having realistic models, pre-computed realistic models of subducting earthquakes and so on, we should include these guys as well. But unfortunately, we don't have much of a database to work on. So I've probably run out of time, and I apologize for it, but thank you for your attention, and I'll take any questions. Preguntas también en español. Thank you.
keep it.
Yes.
Keep it in the questions,
Ah.
Thank you, Emil. We discussed, or you presented most of the phenomenology of the earthquake, but then what would be the tsunami generation mechanism in these different cases? I was wondering whether, for instance, for the tsunami earthquakes, since you mentioned that they are red, lower frequencies, probably the rupture speed is lower, and perhaps you can get a resonant interaction with the speeds of the tsunami. You don't need as much sleep, for instance, and you can still create a larger tsunami. What is our understanding?
Well, the answer to the particular point you raise is no, because when I say that the speed, the rupture speed is slow, it's by seismic standards. So it gets maybe to 1 kilometer per second, 0.9 kilometers per second. The tsunami in the deepest parts, the typical tsunami will be about 220 meters per second, or perhaps even if you go to a very deep trench, it would be 300, but it's still much smaller. So you won't have a resonance, okay? So the problem with tsunami earthquakes is that if you could explore the seismic spectrum of the earthquake in real time to extremely long periods, like 1,000 seconds or more, then there would be no tsunami earthquakes, in a sense, because you would recognize that the moment at this period is very high, and you would use that moment to generate the tsunami. So, and we've made considerable progress, for example, by using the W phase, but the immediate quantification in a matter of minutes following an earthquake is still very much based on short period, on relatively short period measurements, MBMS and all that, which can be deceptive if the earthquake is redshifted.
Okay, so but can I follow up?
Yes.
So if we discard any resonant mechanism, I guess we can still argue that the main tsunami triggering effect is going to be just a large slip and bottom deformation that is going to be transferred almost instantaneously to the water column.
Yes.
Yes, and that will apply also for the blue, the other events, right?
Yeah,
so they still have a large slip or a surface deformation.
Absolutely.
Yes. Okay.
Because they can be very, very large, like in 1933, but in Sanriku, but they they don't hide anything from you. They tell you how big they are in the usual seismic spectrum.
Okay.
So if you look at them from a classical seismological point of view, you don't make too many mistakes. You get the whole information even at relatively high frequencies.
Okay. Thank you.
Any other questions for Emil?
Sergio.
Thank you, Professor. So one of the biggest problems that we are facing as operational systems are tsunami earthquakes.
Yes.
Since we are receiving, and almost all our protocols are according regular tsunamis, megatrust earthquakes, and that kind of things, which also we have some backup systems in case we don't receive information from seismological services, since we are receiving information from perception, intensity, that kind of things. So I read from your presentation the method designed by Newman,
yes.
17 minutes for a solution, which is not good enough for actions in terms of evacuation and issuing bulletins. So do you expect to have any faster information for that
Okay,
kind of events?
All right. So let me address two things in your question, and thank you, because it's very important for us to have a feedback from the operational point of view, the people who are like you on on the front line of operation. 17 minutes was Newman sitting in his office in Atlanta at the time when his algorithm was not automated and so on. So I should have updated this. But now, if you consider closer by stations, you will get the data faster, and you can, presumably, you can do the same kind of analysis with, which is duration versus energy of the P waves. You can do this in probably a much faster time. So that is a preliminary answer to your question. The second point that you mentioned is that you can rely on information about intensity, felt reports, and so on. And that is that goes a bit towards the same. If it's not instrumental, if it's from the population, it would still go a bit towards the same study of a kind of intensity of shaking versus duration. And in some surveys, notably in Mentawai in Indonesia, there were reports from survivors. There were a few survivors. There were reports that, oh, it was kind of funny because it didn't shake very strong, but it shook very long. And this is something which could conceivably help, but it's extremely difficult if it comes from a human perception to evaluate a length of time. So because if you ask someone in the street how long did it shake, and they're going to tell you, oh, it shook for 1 minute, 2 minutes, they have no idea what a minute is. We don't have the perception of time with an accuracy which is good enough for this kind of thing. So I think that in this respect, the answer may lie into instrumenting critical sites not only with seismometers but accelerometers, things which are designed to take a measurement, an instrumental measurement of very hard shaking. So in the case of a tsunami earthquake, there will be a very low signal, but somehow you have to engineer a way of getting the duration of that signal. And an instrument will give you a reliable estimate of duration. A human person may not, but an instrument will give you a human. So I think this would be the direction towards improving and improving this kind of detection and answering your concern and your question. Sergio? No. Yeah. Maybe it's a little late. I don't know.
Yeah. I'm sorry.
Yeah.
Okay. It's a couple of one of them is that when a large normal fault earthquake takes place, the down dip, let's say this down dip, the Chillán, once this 8 point something, 8.0,
yeah.
Do you believe that this earthquake can take place again in the same place, or they rupture the slab in such a way that they cannot repeat, but they could repeat further north or south, but not in the same place? That's one question. And the second is, what's your opinion of Nichenko's sort of a seismic gap theory? After Nankai, the discussion that you mentioned, Ando and Nankai, there are certain places which were more probable to take place earthquake in the future. Mm-hmm. So I wanted to hear your comments on that. Mm-hmm.
Okay, first question, I will answer mostly the first question. We have no idea about the repeat time of these guys. And the argument, and certainly from a geological standpoint, we could make the argument that once it has slipped, there is no strain accumulating for a certain period of time, and so we are safe. But as you say, it could be a little bit further down, and it could be a little bit to the west, to the east, and so on. And since we have no idea about the repeat times, we must assume that these events could take place in the same general framework, in the same general geological province, displaced a little bit north, south, and so on, or in depth. But we are sure about the magnitudes. The magnitudes, we know that they can be very big. Tonga 1977, Tonga 2006, and so on. We know that. Second point is, I think I said enough. I mean, we don't really understand what the future holds. Okay. Thank you very much. Appreciate you all.
Thank you, Emil. Okay, so we have Edmundo Norambuena. He's going to give the next couple of talks. He's going to be talking about the seismicity in the southern region of Peru. First about the GPS, the GNSS network that's operating in southern Peru. And then the seismicity in the northern region of Chile.
Y con el izquierdo retrocedemos.
Buenos días con todos. Sorry, I'm speaking in Spanish. Morning to all. Again, my name is Edmundo Norambuena. I am from the Geophysical Institute of Peru. IGP, as is known, is a government agency that belongs to the Ministry of Environment. Our main mandate as a research institution is to do research in earth science, as well as to implement mechanisms to mitigate the impact of natural disasters. So here on this first slide, I show what we call the seismic ecosystem in Peru, mainly classified by the different types of sources of earthquakes. Now we have the subduction zone type earthquakes, we have the intermediate depth earthquakes, we have the deep focus earthquakes on the very east, the Peru-Brazilian border and Peru-Bolivian border, as well as the superficial seismicity mainly associated with faulting. No? And we have just a seismic map that describes the catalog of several years. Oops, too fast. Of course, my talk will focus a little bit between showing the seismic activity in southern Peru as well as the operational activities that is required to do the studies and modeling. You know, we need data, no? And data requires instruments. So I will focus on how this data is collected in Peru, because the distribution and density of stations, of course, impact on quality data. So here we show what is called the National Geophysical Network. It's comprised with three networks. One is the seismic networks, we have the strong motion networks, and we have the seismic volcanic network. For the seismic network, we have now, or currently, we have 58 VSAT stations, satellite stations that transmit signals directly towards the capital Lima. We have about 300 slow motion stations. Of those, 78 are real-time also to the National Seismic Center. We have a couple of views of the VSAT station also. In case of a large earthquake in Lima that may destroy the capital, you know that we are in more than 80 years with no magnitude earthquakes in Lima. We have developed a mirror site 300 kilometers east of the capital. So we have all what is collected in Lima is collected on this mirror site 300 kilometers off of Lima. And currently we are also developing one in southern Peru, in Arequipa. This is a view of the current seismological center. Here we monitor, as I say, the stroke motion, the seismic activities, as well as the data from the volcanic network. No? Currently we are monitoring 12 volcanoes in southern Peru. This is a view of our headquarters in Arequipa. It's just brand new. It was inaugurated last year. And here we go with the seismicity in southern Peru. This seismicity that is plotted here is between the Nazca, south of the Nazca Ridge towards the Peru-Chilean borders. And the seismic activities, as we saw in the histograms, mainly is concentrated between 4 and 5 magnitudes. As you will see, as difference with Chile, we don't have very large earthquakes in Peru. So, so far, in the 21st century, we have had the 2001 Arequipa earthquake and 2013 Acari earthquakes, magnitude 7, the Acari earthquakes in 2013, and Lomas earthquakes in 2018, both were magnitude 7, as in the 2001 earthquake was magnitude 8.4. This is a view of the distribution of the seismicity. We have plotted the focal mechanism just to show that the focal mechanism is in agree with thrust events, no, in the trench. Yeah, this is another view for the Lomas earthquakes and the intensity distribution. And here I want to refer to an old study of the 1990s of Torbath. It's a very noteworthy study because he, using historic catalogs, he inferred the intensities and developed these isoseismal maps, and from then, with different equations, he reached to associate a magnitude and a rupture length for these historical events since 1582 till 1868. So this is just the plot of the isoseismal map on this paper of the 1990s BSSA. And just to conclude mainly on the table on the right, just to show mainly the 7 earthquakes that occur between the Nazca, southern part of the Nazca Ridge till the Peru-Chilean border. And just to show that for magnitude 7 and 7.5 events, the rupture length is about 75 kilometers, while for the events of 8 and 8.4 or 8.8, as was classified 1868, the rupture length varies between 350 and 450 kilometers. And that agrees with also current studies like the 2001 event. I said that in yesterday also we were talking about that the business of all who we are here is to save lives. So from that point of view, IGP has developed recently what is called the Peruvian Seismic Alert System. Our colleague from the National Geographic Directorate in Peru yesterday mentioned that they have a threshold about 8 minutes to receive the seismic bulletin from IGP. But currently, according to the protocol, that's a maximum. It's not the time that we currently give that information. On average, the seismic bulletin is transmitted after we occur an earthquake is within 3 minutes. So our Navy received within 3 minutes the information about seismic activity offshore the Peruvian coast. However, this system that we are developing in-house has developed about 110 strong motions along the coastal line and has provided intelligence to each of those devices installed along the coast, such a way that as soon as the wave hits the coast, there will be one strong motion that will detect that the P wave arrival, and using IA or AI, it will give a location for the event and an estimate magnitude. But the system will trigger, by a protocol we also will have standardized within DESI and the Navy, it will trigger if the event is greater than magnitude MW6. So, we have the spacing of those stations are about 20 kilometers between them. So we cover the about 3,000 kilometers coastal line between Tumbes and Tacna with these 106 devices, although we have increased recently like 5 more stations along the coast. But the important things of this is that the information that each of these stations act individually. So each station within 3.5 seconds provide information about the location and the estimate magnitude of the event. And that information is transmitted to what we call nodal centers that are 10 distributed along the country, because you know if an earthquake happens in Piura, it doesn't matter to Lima to be informed in the sense of start sirens to announce people that an earthquake is coming. The 3.5 seconds that takes the time to compute the location and the magnitude of the event gives a shadow zone of about 3 times, let's say 24 kilometers from the receiving point in the coastal line. So, and this is also important, no? Because our Navy, for tsunami purposes, so the information also will arrive to the Navy that within 3.5 seconds or 4 seconds, an event magnitude 6 or greater is going on. No? So they can have more time to elaborate, like yesterday we were talking about the world of the models, no? Which model is the better to use for a given scenario of inundation map, etc., etc. So, yeah, this is just a view of these 106 stations that we have along the coast. Are pretty close to the coastal line. Signal is transmitted by telemetry, digital telemetry. In certain receiver areas, we have satellite links to our central site in Lima, in addition to links to each of these 10 nodal places that I mentioned before. We have a simple box within the station that have currently material like power supplies and a small box, no, that is developed in-house. Also, we work in cooperation with our Navy because we use also lighthouse along the coast to house our many of these stations, as well as natural reserves along the coast. This is just a map showing the topology, how the communications are done between the different stations in Lima Center. This is a close view to the south. No? Each station is individual, but signal is transmitted between them until they arrive to Arequipa, to the building that I showed you before. And this project is being done in cooperation with our National Defense Agency. But why is that? Because we as a technical institute, no, we are not allowed to diffuse the information to the public. So that corresponds to the National Defense Agency. So as I said before, IGP has the 106 stations, collect the data, and transmit that to a central site, one of the 10 nodes that I mentioned. And each node is there are like two computers back to back. No, one computer where the information that is collected by the 106 station are transferred to the computer of INDECI, and that computer will decide which set of alarms to trigger and inform the population about the incoming event. However, we are a little delay on this part. We have finished all what is on the side of, we are already emitting alerts from those stations, and we are working currently in a way to use normal broadcast signals from any radio to broadcast our signal there, and we have developed small receivers, like a small just FM receiver radio, to detect the information we send through the national, we call in Peru, we have the Radio Nacional, national radio like NPR in the US, no, that broadcast signals in a given frequency and mostly have the better coverage along the country. So we have used that radio station to mix our signal with the signal of that station, and that propagates to the whole city, and anyone who have this receiver, who currently we have developed at the cost of about about $300, no, can receive this signal, and it triggers a small alarm, and also displays the, also this device, it will trigger only if it is within the radius of alert. Something that I forgot to mention is when the signal came from the 106 stations to the central nodes, there is added one information. What is the radius of impact of this earthquake? How it is done that? It's done using a theoretical intensity map. So we have a magnitude, we have a source, and we have an attenuation curve. So we define what's the distance of the source, where it will be 0.05 g of acceleration. So that's the maximum range where the event could have a significant impact. No? Well, that's the first part of my talk regarding the Peruvian seismic activity. I guess we leave if there is any question by the end. I have also a second talk about the GPS and GNSS networks in southern Peru. I forgot, for the seismic activity and as well for the geodetical aspects, currently we are doing a project with the University of Grenoble. So jointly we have installed, in addition to the geophysical network that we have in southern Peru, we have installed 20 broadband stations, portable for a time span of 5 years. And also 5 new continuous GPS stations having added in the Zoom. Those are depicted there with the blue triangles. And the white and red triangles corresponds to the current permanent GPS network. Mainly this network is composed by donations of Caltech in 2007 and what's called ISTER in 2013 donated Caltech 10 stations and ISTER 10 stations. However, currently only we have 18 of those stations in operation. Also, the square dots there represent survey stations. So we have an average of 30 survey stations that are covering all the southern part of Peru. So given that we started measuring in 2007, we have a very large time series for the southern Peru deformation. And as Shamita Das was asking yesterday, how good is 10 years, 5 years, or 20 years of data? What is best in order to do the inversion for this data? And Francisco told what is known is that the larger the time series, we only reduce the effect of the noise or the sigmas that we call the errors, the formal errors. So that's we have a better time series. So yeah, this is a view of the. Here we have the Caltech stations, southern Peru, northern Chile also, Caltech installed in northern Chile, same kind of stations. We have on the right side stations of type of stair stations, are different kind of antenna heights. So all these instrumentation, the 18 plus the new 8 ones in southern Peru that totalize 26 currently continuous GPS stations in southern Peru that has allowed to obtain these velocity maps. And this is from Lovery et al. 2023, because he's a PhD student from the University of Grenoble. So he's working with currently the full set since 2007 to 2023 with obtaining these velocities and doing the inversion. That's why I'm not dealing directly with that now. And it's a JER paper submitted to JER. And here we have what we do, what we put the stations just to get coordinates in time. Time series are used to plot velocities, and velocity is used to do inversion and see what causes the formation in the surface and obtain a least distribution. So here we just compare the Villegas solution with the Lovery et al. 2023 solutions for southern Peru. Mainly we are focusing only in southern Peru. And we need to take into account that these maps of asperities or seismic coupling is just to show what will be the maximum earthquake that might occur in the zone. And like Esmil was commenting yesterday and today, an event can break as a whole or as a piece. So maybe we can reach in one time the whole size asperity, or maybe fraction it. So magnitudes will be different. So for our tsunami purposes, in scenarios or the modeling world, as I say, or the world of the models, we need to take into account that these maps shows what will be the maximum event, not that will be the maximum event. That is the possible maximum magnitude that an event can happen on that region. So using a system like the one that I showed you before, that we can get a location for the event in 3.5 seconds or 4 seconds compared to the normal 3 minutes that used to take. So now we have more time to do more things, or little extra things. So our Navy, with this information, can run different destinations, giving a location of a particular event occurring between the trench and the coastal line, giving the magnitude parameters, and having these scenarios of maximum coupling. So just to take in mind, the modeling is a world. We change parameters and we have obtained a different forecast. So we need to be which set of model parameters is the best, or which model is the best. So it's something important to take into account. And I put this slide yesterday because my colleague from San Marcos mentioned that doing the joint inversion with teleseismic data, tsunami data, and geodetic data obtained for the 2001 earthquake in Camana, where it was the tsunami maximum height, he obtained a subsidence of about 80 centimeters. And I plot this just to show that it's in the vertical. This is the time series of the IES station of Arequipa in the 7 years, 1994 to just 2001 after the earthquake, just to show that in effect, it was, or indeed, it was the 80 centimeters. of subsidence. So while Arequipa City subside 50 centimeters, in the coastal line were 80 centimeters. No? And just on the right, you have just a view of the velocity field, of the coseismic velocity field for the 2001 event. So I guess this is the last one. Yes, I want to leave with this reflection. I like this phrase that was written in a book for my colleague Tim Dixon, that disasters occur, or you can read it, but I can phrase it, disasters occur not because Mother Earth did something unexpected, but because we human beings live or just decide to live in places that are vulnerable to natural disasters without taking the proper measures to adapt to them. So it's not, the disaster is not caused by the natural hazards, it's because we didn't take the proper measures to live with them. So I guess this is the last one. So I will take any questions if you have any.
Okay, thanks for the presentation. You showed a map with the interseismic coupling, and you said you could define the maximum event based on this map. I was wondering, how do you define the slip, for example, of an event? Because the map showed a value from 0 to 1, right? Not the previous one.
Okay.
The other one. So the interseismic coupling is from 0 to 1, but you said you could define the maximum event or maximum possible event. And how do you define the slip if the event could take place today, in 50 years or 100 years? So the slip would be different.
Yeah, of course. Yes, I understand your question. As I say, the world of models, is I won't say the world of marble, but what is a fact is that we have put GPS stations on ground, and we have just measured its variation a long time. So we are just measuring at a given amount of time, or a window of time, how the Earth is deforming. So and that's the velocity that I plot on the previous slide, the arrows. So with doing inversion, it's just to say, oh, this is the velocity my stations are moving. So what could be, the slip distribution on the plane fault, on the fault plane, sorry, that is causing this deformation on top. So this is coupled, because that kind of slip distribution is the one that is showing me on the surface what I'm observing. I cannot observe in the inner part of the crust or the lithosphere, but we only observe on the surface. Therefore, my best guess is after my data observed on surface and inverted that is this current slip distribution that is showing up. So that's the amount of coupling that exists on the area. So given the size of the sphericity, we can estimate the dimension of the seismic moment, and therefore a given MW magnitude. I don't know if this satisfies you or.
Yeah, but I still have some doubts about how you define the event. But we can continue discussing later.
Yeah, but it's like talking about geological time. We cannot see the window is too long. What we are seeing is just like a small slot in time. And that's what GPS is giving us. It's just a picture at a given amount of time of this long time series. As Emil was showing his slide, stick, slip, but we don't know the periodicity. We cannot talk about the periodicity in stick slipping. We assume that this has a recurrence time, but it hasn't been completely demonstrated.
I agree with you, Edmundo, that it shouldn't. Periodicity should not be spoken in this kind of things, and recurrence is a very loose word in this case. There is one thing that there is to consider, and in that picture that you're showing here is very obvious, and it's a problem with all coupling maps. It's not a problem with this, that you only use on-land GNSS. If you relax the damping parameter, you see that the coupling starts to grow on the near the trench places. And an extreme example is the paper of Loveless and Mead in Japan, where they can put full coupling at the trench and zero coupling at the trench, and they explain very well, both models explain very well the GNSS data on land. So that's something when we have to, when we start making scenarios using coupling maps, we should use that uncertainty. And the problem is that since this kind of inversion are regularized, we are reducing the uncertainty because we are adding more data. That is the prior information that comes with the regularization. So we have to be very careful on how we account for uncertainties. It's not just the covariance matrix of the least square problem. We have to revise how uncertain are our prior assumptions about how the slip has to be. And there are ways to do that, but we can discuss later that. But
I agree with you.
Very nice presentation. I really like it.
My colleague, and I guess Mohamed Chile also, we are going addressing this stuff in more detail. But you have given me the opportunity to point something. What will happen when we do the earthquake location, for example, we have velocity models. So having velocity models, we have given different different thickness of layers and different velocities. So yes, also varying the thickness of the layers and varying the velocities, also we can have more or less same results. So in these inversion models also, I agree, we have a lot of data, and a small number of unknowns. So we have minimum globals, or we have a maximum global, and that needs to be taken into account. So when we apply the lambdas of the move or the roughness of the inversion, of course, that will be the criteria of what we are doing in the inversion, and also taking into account what we know about the history of the area. So my point of showing that our BAF paper was just to point out that there is an average rupture length, and that's important also for tsunami purposes. And having that average length on these asperity maps, or these coupling maps, also we can estimate the size of the possible event that will dissipate that coupling in the future. Of course, I don't have control if this breaks in 50 years, in 100 years, or in 150 years, maybe the situation has varied. But it's what we have now, what we are measuring. And that's the observation that we are trying to just explain why we are observing that. So.
Okay, we have a couple more questions. Gabriel, I think Anne is also online with her hand raised, and I think we have Jorge also.
Okay, so thank you very much for your presentation, Edmundo. This is a nice network, and it will be nice to put together the data that you have from Peru, from southern Peru, with the data that the seismological center has from northern Chile, for example. I don't know if it is possible. This is my first question. Are all of this data available for the scientific community, or this is not possible yet, and why not?
Yeah, the seismic
my
data.
First question,
yeah. Okay, so I answer your first question before the second. Yes, we share currently seismic data with you guys here. So online, we give information. Our southernmost seismic station are shared in line with University of Chile, with the Seismological Center of Chile. Okay. If you refer to the geodetic data, currently is not openly shared, but we are working on that. We are working on establish DOIs or handlers to put the data available for being used. No?
Yeah, that will be great to make the data available for free, in fact, for every scientist. My second question is, thank you very much again. My second question is more a comment regarding the subject of this meeting again. To say the maximum size of an expected earthquake is, I believe that it is a dangerous idea, because I agree when you say, for example, this is a possible earthquake. Okay, because we have, with the data that you have, is what the model can tell you. Okay, but this is a model from data that you are receiving at the surface of the plate, from something that is happening many dozens of kilometers underneath. So it's a model, it's a good approach. I think we need to do that. We learn a lot from coupling maps and things like that, but it's a model. And just an example is the Maule 2010, for example. In that area, we had the Talca 1928 earthquake, and the Maule 2010 encompassed all of the entire region. So for the huge event, it seems that even if we can have some smaller event that have occurred in a period, for the giant event, it doesn't matter. It encompasses a lot of this same region, in fact. What do you think about that?
Well, as I guess I say at the beginning, modeling is a world, because it happens to me the same in the office when I have to deal with my colleagues that are forecasting the El Niño phenomenon. No? They do a model for Kelvin waves or sea surface temperature variations. Say one model A, model B, and model C, and they average the models. So which is the best model? No, that's why I say the world's models. So I think your question is difficult. I don't have a complete answer for that. I guess we need to keep working on that and trying to understand the mathematical inversion is just a tool. It's just mathematics. No? We invert the data, no? But the solutions, we need to tie those solutions to the real physics. No?
I do agree with the methodology. Sorry, I do agree with the methodology, with the physics and all of that. I do not agree with the way we can communicate what our findings. I mean, it is dangerous to say, for example, this is the maximum earthquake that we could expect from one area, because we already had an earthquake just in the neighboring area. This is my point. We need maybe to think on that, but this is my main point.
Okay, thanks for your comment. I guess my colleague Juan Carlos Villegas, who is the map there, can explain a little bit more about, in more detail that. So.
Okay. We just want to have one last from Anne that I think she's online, one question, and then we'll break up for coffee, and then we'll continue with the talks that were scheduled for this segment after the break. So just one last question for Anne. Are you online? Are you listening?
Anne, are you awake?
Yes, sure. Hi. I just wanted to comment on the fact that we will go back to these coupling maps and on the methodology to assess the maximum magnitude. But I agree with the comment that it's always very difficult to assess any maximum magnitude, but it's an exercise that we should do as scientists to have either deterministic views of the maximum magnitude or statistical views of the maximum magnitude. So I think it's quite important, notably if we want to assess the hazard. And definitely we need to assess the uncertainties associated with these estimates. But Juan Carlos Villegas and myself and Mohamed, we will go back to that. So I guess we can go for the break and discuss that later.
Okay.
Okay.
Thank you, Anne.
Thank you.
Thank you, Edmundo.
Thank you all. Bye.
So we meet back here in 15 minutes. Okay, so we're gonna get started again. Make sure we try to catch up with the schedule. So, if you can go take back your seats, so that we can get started. Okay. Okay, so we're gonna get started with a couple of presentations. We made some changes to the presentations, so because we have some people online, and we're gonna move Sergio's presentation to the end of the next section. And so, and we have two additional participants that just arrived, and so I'm gonna hand over the microphone to them so that they can introduce themselves. They're Miguel Estrada and Bruno Adriano, and I'm gonna let them introduce themselves.
Well, still good morning. Thank you very much for the invitation. My name is Miguel Estrada. I come from Lima, Peru. Actually, I work at the Civil Engineering Faculty of National University of Engineering. So our research topic is regarding geomatics, actually. So this is our specialist. And just in a few years ago, we just entered to the study, to the making research activities regarding to tsunami. So I am engineer. I am not a geologist. No, I am not scientist. I am an engineer. But with the engineering, geological and geophysical information that we got from the scientists, we prepare together with DHN, that is the Navy institution who provides the national inundation maps. So we work together with them. Now we are under the support of JICA, the Japanese International Cooperation Agency. And now we are developing some research to improve our inundation maps regarding tsunamis in all over the coast of Peru. So we have almost 2,500 kilometers of coast, and we are very worried about that. Thank you very much.
Okay, thank you. And then Bruno is Bruno. Oh, there you go. All right. So briefly an introduction.
Okay. Good morning. Thank you for the invitation. I'm Dr. Bruno Adriano. I'm an associate professor at Tohoku University in Japan. My expertise, I'm also engineer by training. I have some understanding of tsunami sources and tsunami simulation, but now my main research is in try to coupling numerical simulation and machine learning for enhancing tsunami disaster response. Thank you.
Thank you very much. And so the next, our next speaker is going to be Juan Carlos Villegas, and he. Okay, yes, you're here. Okay, okay, but they have their own presentations later, right? Okay. Yeah, so you need either stand there or take this one. Okay.
So we're going to make a single presentation. So Anne will share her screen. So Anne will start with this presentation, and I will follow her, and then Mohamed. Thanks. So Anne, I think you can go ahead.
So do you see my screen?
Yeah. Can you put in a full screen, please?
Okay. Sure. Yes, I was just checking that. All right. So yes, we have coordinated a little bit, not to repeat the same thing.
Yeah, it's okay now.
And in fact, we already had like some first examples of those interseismic coupling maps in South Peru and North Chile. So the idea is that so we'll talk the three of us, myself and Soke from ISTER Laboratory and Université Grenoble-Alpes, and Juan Carlos Villegas from IGP, Instituto Geofísico Peru. Then Mohamed will do a synthesis. So he's from and ISTER Laboratory. So we have, maybe the positioning of the presentation that today is to try to make the link between interseismic loading and earthquake potential. And example, in the case of the Tohoku, occurred in an area that was affected by interseismic loading beforehand. So this was known before the earthquake, and then the earthquake occurred, and we can see with this model that the interseismic loading was high in the area that was later ruptured by the earth. There were quite a lot of GPS campaigns. So this is a paper by Marianne Metois, a former PhD student. But so it's a paper that was published in 2012. Here, show the seismic load in the Maule segment. Here, were performed before the peak. And what we can see here is that there is a very strong gradient of this interseismic loading in this area. So if we invert this strong gradient, we obtain the following. Of course, depending on the coupling distribution can change a
Hi,
little
Anne.
bit. But you can, yes?
Hello, Anne. Your screen, I think, is freezing.
Yes.
And your audio is also not continuous. Maybe you can switch off your camera.
Okay, yes, I will do.
And your screen is in the second one, I think, in the Japan 2011.
About that. Okay, I will make that.
If you want, I can share the screen here if you prefer, because it's freeze.
Can you hear me better now? No layers.
Hello.
Can you see my screen? Yes.
Hi, Anne. We are going to share the presentation from here.
Can you see my?
Because it's going very slow.
Yes. Okay. All right, but I don't think you have the last version of the presentation.
Or you can send me by mail, please.
Okay. Okay. Go ahead. Yes, I'm trying. Sorry about that.
So, and Are you sending me the presentation?
Yes, I am.
Okay,
Yes.
thanks.
It takes a little bit of time, I'm sorry. Yes. Okay, maybe in the meantime I can continue a little bit. Can you hear me?
Yeah, we can hear you.
Um, okay. So the problem is that I cannot share anymore my screen.
Yes, your connection seems going slow.
Yeah, that's it. It was working well 2 days ago, but. Okay, I've sent the presentation if you want to get it. What if you want, I can try to share again, or you can share it yourself. It's up to you.
I have received your email. I will download it and show in a minute.
If you want to let me share my screen while you download it, I can continue maybe a little bit. At the moment I cannot share my screen.
¿Puede mostrar nuevamente su pantalla del otro lado?
Okay. All right, so as I was saying, so on the left, do you see my screen now? Do you see the Maole thing?
Yes, yes, yes.
So we have like the interseismic GPS velocity field, and this GPS velocity field was measured before the Maole earthquake. So it's mostly campaign measurement that happened in Chile at the time. And when one inverts this velocity field, you can obtain the following coupling distribution. And as I was saying before I was cut, depending, you can have slightly some kind of variability depending on the model, but one thing that persists is the fact that here you have a high coupling in this segment, and here laterally in this area you have a lower coupling. And something that is really interesting is that depending, you can compute the average coupling here, and depending on the model, it will vary a little bit, but in any case, you will have a high coupling in this area and lower coupling in both sides. And interestingly, the Maole earthquake occurred exactly in this segment. So the take-home message here is to say that the interseismic coupling can inform us on the seismic potential, and it can inform us maybe on the maximum magnitude earthquake that we can have. So using space geodesy, we can measure the ground deformation. So here you see the subduction, here you see the plate interface that is locked in between earthquake and that is moving during the earthquake. And by measuring the deformation above this, you can get information about what happens on the plate interface. So space geodesy can be really useful for seismic hazard assessment and most probably also for tsunami assessment. So this is the seismotectonic context of the area. Obviously, you all know that. So it's an area that experienced lots of historical and instrumental earthquakes. We won't go into details because we have seen quite a lot already, and I'm late. So in South Peru and North Chile, we have the following instrumental earthquakes. So this was Arequipa in 2001. Then there was Pisco in 2007, Antofagasta in 2095, Tocopilla, and finally Iquique earthquake that occurred. Still, we have a large portion of the megatrust that has not been ruptured recently since the two large historical earthquakes in 1868 and 1877. And so probably we can expect some kind of rupture in the area. So it's interesting to assess the interseismic coupling in this area to get better knowledge of some kind of rupture scenarios. So I will start with showing old maps that you have seen already, so it will be fast because I will show old work about interseismic coupling in North Chile. So the measurement of active deformation in the Andes has been a long process. So you can see here historical work. So the work of the German colleagues, the work of the Peruvian and American colleagues, the work of the French colleagues. So it has been a very long initiative. So it started with campaign measurements, and then it switched to continuous GPS measurements. And eventually, about 10 years ago, Mohammed took all these velocities and gathered them.
Stay ahí now.
Are they back?
Yes.
Oh yeah, I see the Ivan Luna is host.
Now they need to probably get all the cameras and everything settled. Yeah. Correct.
Oh yeah, there.
Okay.
Okay. So now we need to figure out where they missed.
Hello, Anne. Can you hear me?
Yes. Yeah. So
Can you continue, please? I'm sorry for...
Yes. So I don't know where you kept, in fact.
It was the image of Mohammed 2011, I think.
Okay. So, sorry, it will be difficult to get the take-home message because there are lots of interruptions. Was it this?
Yes, it was.
This slide?
Yes.
Okay. Nice. All right. So this is a combined velocity field in the central Andes that Mohammed did from the historical papers. And what we can see in this velocity field is that we are missing some density here, notably in South Peru. And the other thing is that we can look at the ellipses at all these GPS points, and we see that the uncertainties at the time were quite high. But so it's necessary to do some more instrumentation effort, and this is what we are conducting all together. So another thing, when we want to model the deformation in South Peru and North Chile all together, we mentioned yesterday that it was something that was quite important, notably to know better what happens in Arica. we need, first of all, to have like a combined velocity field that includes data from South Peru and from North Chile. But we also need to have like a proper modeling scheme that takes into account this internal deformation in the central Andes. So this is a figure by Arriagada 2008, and it shows the finite deformation. But the classical way that we do to model this internal deformation or GPS modeling is to do the following. So this is again a figure from Mohamed. So here you see the velocity field, and here you have the component that is associated with the sliver motion, so the rigid movement of the Andean sliver, and here you have the interseismic loading. And interestingly, in Peru, you have a sliver that moves towards the east, and that has an anti-clockwise rotation. While here in Chile, we have also a sliver that moves towards the east, but that has a clockwise rotation. So we immediately understand that there is a little problem here when we want to understand what happened in Arica, because we don't have a boundary limit here, and it's probably necessary to have more robust and more realistic modeling schemes that take into account the internal deformation together with the interseismic loading. And for that, obviously, it's necessary to go towards viscoelastic modeling, I think. But still, we are not there. So what is the effect of this sliver on the coupling? So here you have, again, a figure from Mohamed. So here you have the interseismic coupling that is obtained by a two-plate model, where you take into account the Nazca plate that is subducting below the South American plate, and we do not take into account the sliver. And as you can see, the coupling is very important. And when we take into account a three-plate model, so this means that we have the movement of the sliver that is accounted for, and we have some part of the convergence between Nazca plate and South America that is taken here along the sub-Andean ranges. When this is taken into account, the interseismic coupling is slightly lower. So this has impact on the amount of coupling, and this has impact also on maybe the seismic potential that we can expect. So it's quite important to have the right model. So as I said, one thing that is quite important is to have to complete the data observations. So Edmundo Norabuena just before mentioned that we have done quite a lot of instrumentation effort here in South Peru. So I was lucky to obtain a research grant by the European Research Council. So it was a unique opportunity to deploy big instrumentation effort. And so we did so in South Peru and here in the Atacama area, together with Marcos Moreno and also Francisco Ortega and colleagues. So all these data, we are trying to process them. So at the moment, we are processing all the available data in South America in terms of GNSS, and we are making the time series available when it's possible. And so you can just go here on this website and get the different time series and play with any kind of modeling you like. So I'm gonna just show some old work that has been that has been done in North Chile in order to estimate the interseismic coupling in North Chile. So it's been an ongoing effort since several decades. And notably, in the frame of the PhD thesis of Marianne Metois, we could obtain an interseismic velocity field in Chile. And using this interseismic velocity field, we can model what happens on the subduction interface. So if we take here a cross-section in the area of Maule, for example, we have here the displacement as a function of the distance to the trench, and the dots correspond to the data. And as you can see, the red curve corresponds to a very simple model that is locked between 15 and 45 kilometers depth. And you can see that this very simple model fits pretty well the data. And so it means that in this area, the subduction interface was locked before the Maule earthquake. So now if we take another cross-section here in this area in La Serena, we can have the data here, and we see that the simple fully locked model does not fit the data anymore. So we need to have an alternative model that accounts for less coupling, only 70% of coupling, and that accounts for some deformation within the Andes as well. Here it's not taken into account. So just looking at the data, we can have a first order view of what happens. And then we can do some formal inversion of those data and obtain interseismic loading map. And as I was saying in my introduction, we can see that the recent earthquake that struck Chile occurred in areas that are shown in black here, which means that those areas were highly locked in between earthquakes. So it was the case of the Maule earthquake, it was the case of the Iliapel earthquake, and also it was the case of the Iquique earthquake. So now if we look at North Chile in further details, we can see that the Iquique earthquake is really in an area that was, so it nucleated somewhere here, and then it ruptured this area, it nucleated here, sorry, and it ruptured this area that was fully locked before. And so now if we try to understand the link between the limits of the earthquake and the coupling or any other physical limits, so I'm showing a work by Jorge Jara, who did his PhD in Grenoble some time ago, and he's now in DFZ as a postdoc. And we can see that the Iquique earthquake that is shown here in green has ruptured those highly locked areas. But we can also make some links with the gravity anomaly and also with the bathymetry. So it seems that looking at the geophysics and looking at the permanent features, we can have some estimates of the lateral segmentation that may control the rupture and that may control the arrest of the seismic events. So following this Iquique earthquake, of course, there was a lot of post-seismic deformation. And so here you see an infrared map. So this is the ascending track and this is the descending track. You can see really well a strong deformation following the Iquique earthquake here. And this, I'm just showing that to say that to model the viscoelastic, this relaxation, this post-seismic relaxation that follows Iquique, we definitely need to implement viscoelastic models. And here you can see the effect of only the afterslip, which is the green line, and then you see the effect of the viscoelastic, which is the blue line, and the total deformation, which is the red line. And if you don't take the viscoelastic into account, you cannot model properly the deformation. notably in the years that follow the earthquake. Taking into account the viscoelastic is really important. So Mohamed will go back on that. And another thing that is really important is the fact that we need a low viscosity body here below the altiplano that will account for some internal deformation. And in this slide, I'm showing the effect of the viscosity of this yellow body here. And we can see that depending on the viscosity you assess in this yellow body, you will have very different prediction for the deformation. So it's probably the next step. We need to do interseismic models that take this viscoelasticity into account, as Marcos Moreno is doing since a long time. Okay, so let's do some kind of synthesis. So you have here, as Francisco has shown yesterday, several interseismic coupling models in North Chile. So at first sight, we have the impression that they are quite different from each other, but we can still see some common features, notably the fact that we have low viscosity, low coupling zones that are present in all the models. So we have one low coupling zone here just south of Iquique in the area of the airport. And here we have another low coupling zone in the area of Mejillones, and here another low coupling zone in the area of Arica. But this low coupling zone is less well constrained because we need data both in South Peru and in North Chile. All right, so I will leave the hand to Juan Carlos now.
So I'm gonna use your screen and continue with the presentation. So I will present some work that has been done in the past years and also a work that has been recently submitted for the Southern Peru subduction zone regarding the interseismic coupling in this plate interface. Next, please. Next. So this is the seismotectonic setting of Peru that is characterized by the convergence of the Nazca plate at a rate of about 63 millimeters per year, sorry. And in this area have occurred recently some earthquakes like the Pisco earthquake, magnitude 8.0, 8.4 in 2001 in Arequipa, and Iquique in 2014, 8.1. And also is characterized by the presence of some features in the oceanic plate, the Nazca fracture zone here, and the Nazca Ridge over here. Also some inland fault systems like the Incapuquio here in the Fourier Arc, and in the Subandera ranges also many fault systems. Next, please. This is the earthquake history for the Southern Peru subduction segment. There are two big earthquakes, the 1604 and the 1868, with magnitude estimated in 8.4 for this, 8.7 for this one, and 8.8 for this one in 1868. And when we compare this with the released moment, compared with the Arequipa, for example, we observe that there is still an amount of moment that has not been released completely to reach this magnitude of 8.8 for this one, for the 1868. And also we observed that in the southern ends of this rupture area of the Arequipa, there are still some areas that remain to be released by earthquakes, for example here in the north, and here especially in the southern end. Next, please. This is already the map that I have shown, just to mention that these studies about the crustal deformation have started in the 90s. And then in 2008, we have started a new project. Next, please. Next. And we, the previous one, please. Yes, so this time we have covered all the Peruvian territory. We observed two distinct patterns here. Strong deformation here in the direction of the convergence here in central Peru, and in southern Peru, the same. But in contrast, we observe it here in northern Peru a different behavior. All these velocities are going southeast at more or less the same velocity. Here, 5 millimeters per yard in this direction, southeast. So we interpreted this velocity field on all this behavior as a presence of a block motion here in northern Peru. That is comprised between the trench and the limit between the western and eastern cordillera. All the sites that are here in the Swandaran ranches are behaving completely different because they rotate toward the east with rates of about between 2 and 4 millimeters per year. So we don't know exactly what is the limit of this block motion, but we believe that it's going towards the altiplano, towards the south. So, this map shows us the velocity, the deformation, the actual deformation of the Peruvian territory. That is the contribution of the deformation induced by the convergence, and also the internal deformation that Anne has talked before. That is evidenced by these GNSS velocities. Next. So based on that, we have proposed this schematic block motion. Here we have the Peruvian sliver that we call like this red area comprised between the trench and the boundary between the both cordilleras here, which is going from 4 to 5 millimeters per year in this direction. And the green area, that is the Swandaran ranches that are accommodated by the thrust faults that we have here in the Swandaran ranches, and the well-known Norandean block that we have here in the Ecuador area. Next, please. So by correcting this GPS velocity field by the internal block motion, we have inverted the displacement, and we retrieve the interseismic coupling map that we see here. There is a large coupling area in central Peru area that correlates well with the rupture extent of the past earthquakes, the 1966, 1940, 2007, and 1974, and also with the great earthquake area in 1746 in central Peru. So this is the most worrying area currently in Peru. Lima is over here. And another striking result is the very low coupling that we have in the north here, and is coincident with the occurrence of tsunami earthquakes, like in 1960 and 1996. And in southern Peru, this is the area of the 2001 earthquake here, that is, at the time was relocking. And there are two areas in the extreme of this 2001 earthquake, here in front of Nazca, and the other one here in Tacna and Ilo. Next, please. I will skip this one to explain at the end, the next one. And recently, since with the help of the colleagues from ISTER, we are implementing a network in southern Peru. Now it's composed of 80 GNSS points, 50 continuous here in southern Peru, and around 30 surveyed sites that are being measured since 2007. Next, please. This is the GNSS time series. For example, for this one, for Lagu, we observe the effect of the post-seismic of the Pisco earthquake here. Pisco is over here. And then it takes, again, the deformation of the interseismic. Then for the rest of the stations, we observe also the horizontal displacement that is caused by the formation of the convergence. And here, for example, in these other stations, we observe the jumps associated to the Iquique earthquake, for example, here, and also in this station in PMCA. Next, please. We have modeled this time series by implementing this trajectory model introduced by Davis and Brown, with different components, the interseismic component, seasonal, coseismic, the after sleep, and also viscoelastic and antenna changes by this equation. And we could reproduce very well the trend of the time series. Next, please. This is another example. For example, for the Arequipa earthquake, here we have the earthquake in this jump, the 2001, associated to this earthquake. Before we have here the deformation. And then we observe very well here that the post-seismic effect. And when we compare the slope of this time series to the current deformation, we observe that there is still we don't have the same amount of deformation, for example, but depend of the reference frame that we took into account. There are 15% in the South American reference frame or 30% in the Peruvian sliver reference frame. a difference, no, regarding to with compared with the previous pre-2001 value. Mohamed will explain a little bit more about this. Next, please. And this is the GPS velocity field with respect to the stable South America. As we see here, we observe the motion in the direction of the convergence, all the velocities. The difference is only the red ones are for the continuous GPS sites and the blue ones for the survey GPS site. And here in these profiles that are cutting perpendicular to the trench, we observe the model, no, a simple model that is fitting very well the GNSS velocities. So it means that the plate interface is locked from the trench until 40, 50 kilometers depth. Next, please. When we model the GNSS velocities, there are some residuals that are not well explained. If we took into account the stable South American reference frame, there are some residuals, as we can see here, in the altiplano that are going southeast. And that was the problem that was pointed out, and that we need to incorporate the presence of a third plate, in this case, the Peruvian sliver. When we introduce or when we correct this Peruvian sliver in the GPS velocity field, we reduce significantly these residuals here. So there is again the contribution of the convergence and the internal deformation induced by the Peruvian sliver that needs to be taken into account to model the interseismic coupling. Next. And then we model the coupling, taking into account this correction. First, this model series of models are the difference between this one is the smoothing that we authorize in between the models. This one for 15 kilometers, 30 kilometers, and 200 kilometers, and the three models are very similar. We identify a coupling area here in Lima, but from the Nazca Ridge towards the south, there is the area in front of Nazca, for example, here that is accumulating stress, and the other area here in front of south of the rupture area of the Arequipa 2001 earthquake in front of Hilo and Tacna. No, and we observe the same here in this other model and this one. And we observe also that the velocities are fitting very well this series of models. Next, please. And when we introduce the Peruvian sliver correction, for example, we retrieve approximately the same model here, as you can see. The same area here in front of Nazca and the other one here in front of Hilo. We run a series of models that are authorized by the data. These three continuous lines represent the models in the Peruvian sliver reference frame, and these other ones in the stable South American reference frame. So we are accumulating stress, for example, in this area in South Peru, in this order of moment deficit rate, which is equivalent to earthquakes of 6.4 to 6.5 every year in this area, for example. Next, please. And finally, and we find also some correlation between these structures that we find in the oceanic plate, the Nazca Ridge, where the interseismic coupling reduces significantly. We found that in the previous studies as well. And now we have implementing a very dense network in this area in the Nazca Ridge to see the real contribution of the plate interplate coupling, and also with the Nazca fracture zone, as you can see here. So the area that remains to be released by a next earthquake is here, and we observe that there is an strain accumulation here in the plate interface that is important. It's accumulating energy in the order of 6.4 to 6.5 every year in this area, and the same in this small portion north of the 2001 Arequipa earthquake. So I will pass the word to Mohamed. Thanks. Mohamed?
Yes, sir. I will share my screen.
Yes, yes.
Okay, can you hear me?
Yes.
Okay, so thank you, Anne, Juan Carlos, for all this explanation. So you all have better understood what are the different limitations that we have in terms of observation and how a similar different model can explain a same data set. I would like to show this first slide that you all know more or less, but this is the contact between the two plates that we see here. And I just reported at the surface the trench here and the coastline. So this is the Nazca Ridge in this region, and we have about 500 kilometers long in this direction and 200 more or less. The coast lies at about 200 here in Lima and about 100 kilometers near the Nazca Ridge. So in this area, we have a distribution of asperities that we don't know at the beginning, and we try to find where they are more or less located. So basically, there are different sizes of asperities. They are more or less closer, the one from each other. And from this distribution, we try to give some information, both from when an earthquake occurs, of course, and but also when it is supposed to be locked during the interseismic. So just to give some basic idea that you all know, so magnitude 6 will break potentially. This is just a simple schematic view of that. But 6 can break a very small asperity of that size, let's say. Magnitude 7 will break a much larger asperity with much more slip. If we consider magnitude 8, it can break a group of nearby asperities like this. And of course, if you have the big one, what we call the maximum magnitude earthquake, it will break the whole section. And we don't know exactly today what control the fact that this one break only one piece, a group of pieces, or many pieces together. So when from the maps that Juan Carlos and Anne have shown, you can see at some places that we can find some big red patches that appear in the area where we think that there is a high density of asperities. But in the Coupling map, you will see here like a big patch. You will see another big patch here, and maybe here you will see like a creeping zone. But you see, if the reality is the distribution that we see below, it's not totally true. The big patch can be also decomposed into smaller pieces. Okay, so the reason I am showing that is that in fact the magnitude, the final magnitude of an earthquake will depend, in fact, of how many asperities will break together and how many displacements will occur on each of these different asperities. When we are inland and deploy instruments that are located at 100 or 200 kilometers from the trench, I think we are dreamers if we think that we will resolve very clearly the very small details that we have very near the trench. Potentially, we can say what happened at this area, with, and more we will be closer to the trench or on the top of the different asperity, better we will be able to describe that. But what we have so far is mainly inland points, and we have to give some guess of what would happen in this area where we do not really have a direct observation on top. So it is important to keep that into mind, and the density of observation here is relatively important, but also the deployment of seafloor observation to be better able to give a better resolution of all that. One way to show that is that One example of that is the Japanese earthquake. So you can see here on left the INSAR data related. The small dots here indicate the GPS station that they have inland. And what you can see here, this is a section that we report here for the INSAR data and for the GPS horizontal and vertical data here. On top of that, I have done a few direct model with different slip amplitude, like 20 and 30 meters. And what you can see is that most of the points that we have here, we can only give some information on the tail of the model. The maximum gradients that occur during earthquake occur mainly in the sea area, and without few deployment of seafloor GPS points, we will be really not able to provide a good information about this earthquake. Another way to illustrate that is by a checkerboard model. So you start with this checkerboard that you all see in below, and you do some inversion at the INSAR point measurement or GPS point measurements inland and in the seafloor, and you can see how each different data set have the power to resolve or not different patches on the slab interface. So you see that it is important to have not only a very dense observation, but also a spatially homogeneous observation to improve what we know today, and this is especially very important in subduction zone where the trench to coast distance, like here for Japan, is about 250 kilometers. So another important point to keep in mind, so to join a little bit the presentation of Emile Okal earlier, before that the Sumatra and the Japanese earthquake occurred, we have many beliefs about the age versus the plate convergence velocity and how the big earthquake are aligned on this plot. But we didn't think that an earthquake can break, like for Sumatra here, more than 1,000 and nearly 500 kilometers long. We didn't think before the Japanese earthquake an asperity can slip as much as 50 meters. So we have many beliefs due to some different observation, correlation we have. And suddenly all these beliefs vanish when a new earthquake occurs. So we are a very young science field, and we are still learning, I think. And we will still learn in the future earthquake, probably. Just by comparison, I have reported here other earthquake that occur in South Chile, the Valdivia earthquake, 9.5, the Maule earthquake. And one thing also to keep in mind is that a magnitude 0.2 difference in moment magnitude significates a moment that is twice larger here than here. So what you can see is that if we take the Tohoku earthquake, it breaks only about 400 kilometer long section, since the Maule break a much longer section, but with much less slip. And at the final result is that the energy released here is twice larger than the one released during the Maule here. So this is something that also should be kept in mind. So we didn't know that it could slip 50 meters, and why not happen in the North Chile or the South Peru in future, we don't know actually. So another important point that Anne and Juan Carlos have shown They have showed you that in detail for the southern Peru and for the northern Chile, but we see that characteristic nearly all along the South American plate. And we see that in the areas where the ridges and fracture zone enter in the subduction, this area corresponds to the extremities of great earthquakes. We also see that this is consistent with a low coupling, as Anne and Juan Carlos shown earlier. And in this paper of Marianne Sayar, she have dated different marine terraces, and this marine terraces seems also to indicate some extremities and barrier of a great earthquake. So this is an interesting morphological explanation to explain what control this different segments and the size of the potential maximum magnitude earthquake. Of course, I added this slide from the remark of Francisco earlier. We should always look at this kind of maps at the same time of the resolution map to see where are the well-resolved patches, but also we can see that in some places, some patches are totally lost, like here in the South Peru, and it is better when we go near the Nazca here. Why? Because the trench coast distance is only 100 kilometers here, and here it's nearly 200 or more. So in the which is the case also in the Arica. That's why in this area it's more difficult to have a good resolution of what's going on. So now, so from this classical coupling map, you can of course take any asperity and do different scenarios of earthquake from historical observation or even more larger events. This is what we call the deterministic approach. And this deterministic approach can be also mixed with some statistical approach that are used today. And for that, if we take a seismic cycle like the one that you see here, so you can partition what occurs during the cycle between different terms. So you have what we call the interseismic, which is the ratio of slip deficit in the interseismic period to the long-term slip. You can determine similarly what we call the seismic coupling by opposition to the interseismic coupling. And you can also determine what we call aseismic coupling that occur during the post-seismic period in after slip manner at the contact of the plate, but also in a viscous manner as Anne have shown, and I will show some picture also later. So one condition to make this cycle, the closure of the budget here on the long term, can be done if we consider that what is on one side accumulating is released through different transient events that can be seismic or aseismic here. So this term here corresponds to after slip, and the ECC corresponds to slow slip event. So using this condition to the closure of the cycle, we can now try to use what we know from the different modeling of the cycle and put some constraint on the frequency magnitude classical plots that are used to determine the seismic hazard anywhere. So what you see here is this plot, and this relationship gives you some line like that, and you can give some prediction. This is the way what it is done today. But now with all the knowledge we have from the seismic cycle, we can put some constraint on that And using the Molnar 79 and AWOC 2015 method, we can put some constraint and draw this line here, which is the frequency of the largest earthquake. And this linear term is described here, and it is composed by the B value that you find from the seismic catalog that we have, from the interseismic moment deficit that is computed from interseismic coupling maps, and also a parameter alpha that is a ratio between the transient slip, and this is the fraction of slip that is seismic over all the transient slip that occur during the cycle. So using this different term, we can put some constraint on the classical Gutenberg-Richter region. If we apply that to the southern Peru and northern Chile segments, so the northern Chile is the segment that goes from the Mejillones Peninsula to Arica, and the southern Peru is the one that goes from Arica to the Nazca Ridge. Yeah. So the classical Gutenberg-Richter law from southern Peru gives us different B value when we analyze different catalogs. You can see here this value. One of the problems using only this classical method, so which is based on the knowledge of small earthquake to determine large magnitude earthquake, we need to have first a very good seismic catalog, and which is not the case actually. We have just some incomplete knowledge of the catalog since the 60s. They are missing a lot of small magnitude earthquake. We have always a cutoff between 4 and 5 magnitude. Also, this typical manner of providing maximum magnitude and recurrence time do not take at all into account the velocity of loading of the system. This is what we are calling the moment deficit rate that we compute from an interseismic coupling map. And it also does not take into account all the slip that is aseismic and that occur during the post-seismic period or slow slip events. So for the Peru, Anne and Juan Carlos have showed you in detail these different maps. So you see here how these maps have evolved with time and with the inclusion of many new observations, increasing number of observations. We can see some principal characteristics like the low coupling that appear in any of these maps near the Nazca Ridge. But even if the spatial pattern can slightly change from one model to the other, one thing that remains relatively stable is the moment deficit rate associated to these different models. And very often we propose a minimum magnitude moment deficit rate and the maximum one with potentially more coupling near the trench to not exclude this extreme case because we have low resolution in this area. But when you look at all these models, you see that the moment deficit rate is always is always bracket in a small in a smaller segment, and that we have a relatively good estimation of that, and it does not change much from the very initial models to the last one that are better in terms of observation. So this is about the coupling model. One point also that is important is the difference that we could have using a different seismic catalog. So here you see the ISC catalog and the IGP catalog. The parameter between these two models are exactly the same. The only thing that changes is the catalog and the B value. All the other parameters are the same. I mean, the moment deficit used in the two, the alpha parameter. And what you see is clearly, depending on the seismic catalog, we have a maximum magnitude earthquake that is quite different. And we can jump from magnitude 8.5 to 9, depending only on this catalog. If we look now, especially on the parameter alpha, that gives you a ratio between seismic slip over all the transient slip. This is this ratio. When alpha is 1, it means that the subduction will release the energy fully seismically. And when alpha equals 0, it means that the contact is tripping and there is no seismic energy to release there. So this is the true extremity here. And so this is for the IGP catalog in green. And in blue, this is for the ISC catalog that we have here. And you see that when we vary this alpha parameter, the maximum magnitude also can vary quite significantly. So you see the influence of this parameter alpha and the importance of taking very well into account a seismic slip, which is not done in the classical seismic hazard method so far. So here, by varying different parameters of all the modeling that you have seen earlier, and by using some classical tree combination, what we find here is that the maximum magnitude earthquake in the south of Peru, from Nazca to Arica, is somewhere between magnitude 8.4 and 8.9. So it's not very well constrained, but we still have this range. And and the main uncertainties here are, of course, what I showed you earlier, the d-value of the seismic catalog and the amount of seismic slips you take into account. Let's jump now in the North Chile. So you see here 7 different, 7 models of coupling. Yes, each model looks quite different, and clearly now that the Pisagua earthquake breaks, many people think this is the next gap. But if you give me all these figures and I have to bring some comment, so of course here it seems continuous and you will imagine that it breaks at once. But in other models like this one or this one, you can see much smaller asperities, and maybe the next one will not break the whole area here, but will break individually each of these different asperities that seems to appear in the most recent models. Another thing is that the next one can also break the missing gap, but also the Pisagua gap. It is not excluded in my point of view. So this is also a similar study that have been done using this combined deterministic statistical approach. And what the people have found here for the northern Chile is that the maximum magnitude earthquake that can occur using the seismic catalog, interseismic coupling map, and the different knowledge we have, they found a maximum peak for the Mmax of 8.8. But we can have up to a magnitude 9.1, but with a very, very small probability of 2%. So the Mmax have a probability of occurrence, and the one that have the most, the higher probability of occurrence in Mmax is magnitude 8.8 for this region. And what they conclude in their paper is that in the next 30, 100, or 1,000 years, we can have a magnitude of an earthquake of this magnitude or higher. The probability to have that in 30 years is 1%, in 100 years it's 4%, and in 1,000 years it's 29%. So as well in the different graphs that are here, you can see how the maximum magnitude can vary regarding that we take a fully locked area here, or the current model that is here, or a fraction of this moment deficit rate. So this is the influence of the moment deficit rate. Here, this is the influence of the alpha parameter that you can authorize in your observation. So this can be determined in the long term only from permanent observation and from very good quantification and measurement of all the transient slip that are seismic or aseismic. So, and finally, the B-value of the catalog, you can see the impact. Lower is this B-value, lower will be the maximum magnitude earthquake. So you can see that to determine the maximum magnitude earthquake, it's not easy because we need permanent observation at a very long time scale and to quantify these different parameters that enter into account here. So some challenges in terms of modeling is what Anne have introduced. Of course, we should take better into account the rheology of the medium and especially the viscosity of the mantle, potentially also the presence of fluid in the medium, and check what is the best rheology that explains, is it better a Kelvin or a Berger rheology that can explain the deformation we measure today. And we need some integrated model that also that explain as well the short-term model, like the GPS, or the long-term observation, like this the rotation here that have been published by Arya Gada, the long-term rotation blocks. Here, this is an example about the effect of viscoelastic on the interseismic deformation. And you can see here the description of the different blocks, as Anne have described earlier. And the three curves here are examples that are taken from the Nankai subduction zone. And the time is in color. It is the time after the 1946 earthquake. So we measure actually more or less the observations that are marked here by the dots. And you see how different viscoelastic model, taking into account a mantle viscosity of 10 exponent 18, 19, or 20 Pascal second, how this different mantle will deform the Earth at different time step, every 5 years here. So what you see is that with this type of mantle rheology, viscosity, sorry, the deformation will be very, very strong, and we may be able with a permanent GPS to measure the evolution of this deformation. You see then here a 10 exponent 19, so the yellow, we are actually in the yellow part. You see that this model can explain relatively well the actual deformation. And when you take 10 exponent 20, you have mostly a rigid body here, and so it gives us some constraint on the rheology of the mantle. So this is maybe something that needs to take into account to better estimate the interseismic in the years that follow the earthquake. And this moment deficit on the long term may also have an impact in the determination of the maximum magnitude. Another thing that might be important in terms of observation challenges is using convolution, deconvolution to localize more precisely the seismicity, and artificial intelligence to better relocalize that and work with some better geometries, which has also an impact in all the modeling that are shown by different authors, but also in the tsunami generation, since the deep angle is important in the vertical deformation produced by earthquake. Finally, I will finish with some new data that are actually processed by the formatter group here in France in collaboration with some Peruvian and Chilean colleagues. So these data have been processed last year. They are collected from a European satellite and put here together with all the different stations that have been deployed and explained, detailed by Edmundo earlier, Anne or Juan Carlos. So what are exactly these data? They are composed of different Sentinel satellite tracks. So here this is ascending track. The satellite is looking on the right. And you can see how this is the average deformation of the last 7 years. So you can see that here in ascending track and here using descending track, so in that sense. And you can see here, for example, in red, a signal that is linked to the interseismic loading, to the post-seismic of Pisagua, as Anne have shown earlier. You can see here a small magnitude 6.2 earthquake that occurred in Peru, in the Altiplano. And this big red point here is an inflation that is around the Sabancaya volcano. So there are many information that are given by this data set, and we are thinking to integrate that together with the fieldwork observation to improve the model in the future, both for the subduction and the internal deformation that affect the continents. So some concluding remark here. What Anne and Juan Carlos have shown is that highly locked patches show the location of seismic sources. The low locking patches indicate some barriers. So these barriers are not very easy to map because sometimes two locked patches are so close then this barrier remain in what we call a stress shadow, and with only some observation at 100 or 200 kilometers away, it is difficult to image these barriers. We see that we have some barrier that seems to be relatively strong, like the Nazca Ridge or the Arica Band or Mejillones Peninsula. And some others seems to be relatively weak. Sometimes they have the ability to stop a large earthquake, but sometimes when the maximum magnitude one occur, they will break. So we are just learning about all these barriers. We don't know really well where they are located. We don't know what are their efficiency to stop or not a large earthquake, and probably we need in a future of many centuries to do a classification of this barrier, as well of the different asperities that break during earthquake to know how much specific asperity can slip, if it can slip 5 meter maximum or maybe 50 meter like we have all witnessed in Japan in the last year. So the maximum magnitude earthquake, as you all understand here, is really depending on how many asperities will break together, individually, and the ability of the rupture to jump like an animal, the different barriers that we have here. Some uncertainties and challenges, so I repeat what I have said. So some challenges about observation, seismic catalog, including a better rheology in the modeling and better quantifying all the seismic slips and transient slips that occur in this area. So that's it for me. Thank you very much.
So any real quick, we can just take a couple of questions for either Mohamed or Anne or Juan. Any questions for any of them? Okay, Raji, go ahead.
Thank you so much, Mohammed, for giving so interesting and valuable information. So this will be interesting, you know, actually in seismology, we generally, at this moment, we generally using the seismic data and using them statistical methods. And that is the practice is going on for estimating the hazard, and which is an important parameter. MMX is an important parameter for assessing the seismic hazard. So at this point of time, what we are doing some, you know, statistical methods. Several papers are there in BSSA or some other journals, so we are using that. So here actually we see that you use the sleeps and others. I am not actually getting properly, but you use some sleep distributions. So and then estimate the maximum magnitudes. So actually I want to understand this little bit. Can you explain this, how it will how this MMX has been calculated by using the sleep distribution? Can you little bit explain the MMX?
Yeah, the MMAX, how you determine the MMAX. So the MMAX actually is the intersection between the Gutenberg-Richter curve that you obtain from a catalog like that, okay? And you will have a line like that will cross your Gutenberg-Richter distribution, and the intersection with that line will give you the MMAX. So you can see here heat. So here we have reported the data in the dots.
Yeah.
Okay. So this is given by the seismic catalog.
Yeah.
And the blue line here is given by this relationship, the return period of the maximum earthquake. So it includes the B value of the catalog, the alpha parameter that you take into account.
Okay.
So this is a fraction of slip of what is seismic.
Yeah.
The fraction between seismic and not seismic, but the fraction of the slip that is seismic over all the transient.
Okay.
Transient is seismic and is also a seismic. Okay. So this is the alpha parameter, and the moment deficit rate that you compute from any interseismic map. This is the integral over specific surface. So here, as I said at the beginning, for example, for South Peru, we take a box here.
Yeah.
This box, and we take all the seismicity in this box, and we compute the moment deficit also in this box. Okay?
Yeah.
So this is the way we do it for this box. But of course, this relationship holds for any point, or you can integrate that all along the South America. You can do it in different boxes. Okay? So here what we managed to show is only for the South Peru and North Chile boxes. For this example here.
In fact, you do a moment balance between using the geodesic. So you use the slip deficit that you compute with the geodesic. You have a moment balance, and you do this moment balance against the seismic catalog.
So this
intersection between both gives you the maximum magnitude.
So this calculation is considered the seismic data also. Seismic data, A, B value, and also the slip information. All this contributes your maximum magnitude. Is it? Yeah?
Yes, all you contribute.
I think it is more, more informative, because at this moment we only use the seismic catalog, and from the seismic catalog you use generally the maximum magnitude. So, but this will be.
This is what
this is
everybody do. You know, in France we have determined this to construct nuclear plants. You know.
Yeah.
Look at these maps, seismic catalog. But today, with all the information we start learning from geodesy and from different aspects, you know, from when we have permanent observation, we can catch transient events that do not radiate seismic energy, but aseismic sleep. And this contribution is important in the long term to improve the seismic hazard.
Yeah, this would be important.
This approach, you only use seismic catalog, and this approach do not really tell you where is logged the area. So in the coupling map, you have two information. You have an information, partial information of the area that are more locked, and you have also a moment deficit that is the integral of that, multiplied by the coupling and multiplied by the plate velocity. This is what we call a moment deficit rate, and it is given in Newton meter per year. Okay. And so, if you want to have the moment on the long term, you multiply by a year, and you have a moment.
Thank you so much. Yeah, I understand this point. Yeah.
Okay. So one last question here.
Thank you, Anne, Juan Carlos, and Mohamed for this nice presentation. It was very interesting. I have some question regarding the. I don't understand if it is your proposal or not that, for example, 8.8 magnitude earthquake will occur in a time recurrence in the range of several hundreds of years, several thousand of years. I mean, and just to finish, this is my first question, and related to that, what about the possibility for a 9.5 earthquake along, for example, northern Chile? I ask this because we have increasing evidence about a huge event along northern Chile. Of course, we presented all of this yesterday. And regarding this proposal that we have, this barrier, Mejillones barrier, will be not, has a barrier regarding this huge event. This is the first comment. And